Okay, awesome. So guys, a very warm welcome to the geometry workshop. As you know, this has gotten pushed from last week, and but it should be good to go for today and tomorrow at least. So again, just to reiterate the point I made by starting the session last week as well, right? That the intent behind the session would be, and it may be useful to just align with everybody here on what they can look forward to within these sessions and like what are the intended outcomes, right? So in terms of the content of this workshop, we'll cover the theoretical concepts and we'll also cover uh, a very wide variety of problems as well, right? And again, obviously, I know that most of you would have, undertaken the course on geometry or in general quant itself before as well. So this might be more of a revision, but hopefully you also get to know some things that were probably either missed out or you're not able to recall or something, right? The intent behind having this for geometry was that geometry typically is one of the areas for quant where some people like develop an inherent resistance, at least like even if they know a certain concept or they know a certain theorem, a formula, but while applying it in a mock in a time frame of let's say 2 minutes, 3 minutes, or whatever, they sort of struggle, right? So, and that has to do with a lack in the variety of problems that they've gotten exposed to probably. So, this workshop is intended to address that, and like that is the reason why even when we'll be doing the questions here, like when we go through the questions, the system would be such that you'll get like 2 or 3 minutes exactly to give it a shot or to basically just strike that okay, what is the concept getting used to solve it, and then we'll discuss the solution in detail. But please treat each question like in a sort of a mock environment, right? And of course, before we get to those, we'll obviously cover the theory as well, uh, so that there is a revision in place. Cool. So any questions, or we can start? Awesome. Should take that as a no, and I'll present my screen. Cool. Is the screen visible?
Yes, sir.
Okay. Fantastic. Cool. So let's start with the revision of concepts, right? With the probably the vastest topic in geometry, which is triangles, right? And again, please, like there's no ground rules for this session. Anytime you have a question, just like you don't pile it up for the end, just interject me right then and there and ask. It's a smaller group, so there should be no hesitation as well to ask questions, right? So okay, so starting with triangles. Now, triangles, there are 3 or 4 sections of concepts basically. The first section is probably what I maybe term as a basic section in terms of the sine rule, cosine rule that everybody knows, right? The A by sine A equals B by sine B equals C by sine C. And again, let us just have a standard figure as well to the side so that it's there for common reference. The side opposite vertex A is small a, opposite B is B, and opposite C is C. This is the sine rule as we know it. The portion of this which some people do miss at times is that each of these is equal to 2 times the circumradius, the capital R. This is the complete sine rule, right? Like typically what we apply is generally only one angle known, one side known, and then we sort of apply sine rule directly, but each of these is also equal to twice of capital R, where capital R is the circumradius. So this is the sine rule. The cosine rule is, as we know, let's say for cos A, if we write, so it will be the sides that are joining at A minus the side that is opposite upon 2BC. So if this was vertex A, so basically B square C square minus A square upon 2BC. So again, pretty fundamental, nothing groundbreaking over here. Right. So these are the two properties that you'd see sort of intermixing geometry and trigonometry in a way, right? So this is there. Then we come to the next meaty part of
QR is
yeah,
this one, right? R
circumference.
means Circumcircle, okay.
Yeah, so let me just write down. It's a good call out. So it's just circumradius. So basically, if I draw a circle around this, the radius of that would be the capital R, and 2R is equivalent to each of these, right? So and there's the cosine law, right? Now with this done, this is sort of the basics. Now again, since it's the starting of the session and probably the attention span is higher right now, so let me get to a slightly tricky part, which is the part on the centers of circles, right? Centers of triangles. My apologies. So right, and this is very important because this is where sort of people tend to either confuse or not be able to apply properly, or they just don't know some of the principles here. So there are like 3 or 4 basic centers of triangles. The most common, like, and I'll just write them down just for reference. So one is the incenter, one is the orthocenter, one is the centroid, one is the circumcenter. There is a fifth one as well that we'll discuss, but that generally isn't as common, which is the excenter. But we'll discuss it just for completion's sake. Right. Now let's go through this one by one and try to understand and grasp the important properties of each from an examination standpoint. And whatever we discuss here, no concept asked in CAT will go outside of this. So maybe helpful to keep this in mind. So incenter, first of all, very important. It's by definition the meeting point of angle bisectors. Right. So let's just draw it as well. Bisectors. So basically, if we have a triangle here, BC, and there are 3 angle bisectors here meeting here. So this is the point I, which is the incenter. And again, since this is angle bisector, these angles are getting bisected. So these would be equal. So that's the first, that's the definition of an incenter, right? The radius with respect to this, basically the circle, if you draw a circle through the 3 sides of a triangle, this is called the incircle. And the radius, basically this distance is called the in radius, right? Usually it is denoted by small r. And again, since this is the radius, this is, and every side is a tangent, so this is 90 degrees. Similarly, this is 90 degrees, slightly displaced, but yeah, you get the drift. And this is 90 degrees. So I to any side, the perpendicular distance of incenter to the side is equal. Perpendicular distance from I to sides is equal. And this distance is called small r, or the in radius. Yeah, please go ahead.
The circle for the incenter is the circle that touches all the sides of the triangle, right?
Exactly. Yeah. I think somebody is there. Just a second, let me just check. Okay, maybe it's this. Is somebody in the waiting lobby? Yeah. Okay. Cool. So yeah. So to your question, yeah, let me just draw it once again so that there's a clearer image probably. So here, this is the circle, this is a triangle, and this is the circle. So there are 3, it touches all the 3 sides. It touches this side here, touches this side here, touches this side here. So this is called the incircle, and the center of the circle is called the incenter. So incenter is a center here. So of course, if it's the center, then these distances will be small r. This is small r, and this is small r, which is the same. So we say that the perpendicular distance from incenter to side is the same, which is denoted as the in radius or small r. So this is the basic definition of what the incenter is, because it may happen that the question might not categorically say that it's an incenter. It may say that, okay, that the angle bisectors meet at so and so point, right? So you have to understand from that if the angle bisectors are meeting at a point, they are referring to the incenter. And so from that point, the sides will be equidistant. So that is why we're covering this definition. The most popular formula around the incenter is around the in radius, which is R is equal to A by S. A is area and S is semi-perimeter of the triangle. Right, and S is basically so A plus B plus C by 2. Now again, this formula everybody remembers, right? But the thing that they don't remember about the formula is that this is valid for all geometrical figures. It's not only for triangles. Even if you apply it on, let's say, a parallelogram, a rhombus, any geometrical figure, even a trapezium, etc., this R is equal to area by semi-perimeter will always hold true. So just keep that in mind, because it may like happen that okay, you may be able to apply this in some question, even if it's not a triangle question. Right. Okay.
So, sir, my doubt. So, sir, in that case, also the circle will be touching all the sides of that polygon.
Absolutely. Yeah, absolutely. So for example, like if we have, let's say, a rhombus, like just an example, right? So there'll be a circle that touches all the sides here, something like this, right? So the center of the circle will be the in center of the rhombus. So the in center definition stays the same, just that the figures that we apply it to are get different. Like here it was triangle, it was rhombus, but definition remains the same. Here again, the sides, the distance to the sides will be equal. R, 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 R. And this R also will be area upon semi-perimeter.
Right, sir.
Okay, awesome. So now, so this is the formula for the in radius as such. The other formulas relating to, since we are talking about incenters and angle bisectors, let's also basically document the formulas for the angle bisectors relating to angle bisector. Let me just create some space. So hopefully you would have made notes. It's not working. Okay. Right. So now after incenters, right? So incenters meeting point of angle bisectors. Let's understand angle bisectors for a bit. Angle bisectors by definition is obviously like which sort of cuts the angle into two equal parts. Here, this would be an angle bisector. If this is theta, then this would be theta. Similarly, there will be an angle bisector from here. Again, this is like, let's say x, this would be x, and so on and so forth, right? Now, the angle bisectors have a couple of important properties to themselves. The first and the most important is called the angle bisector theorem, right? Angle bisector theorem, which says that AD, which is the angle bisector from A to BC, so this particular angle bisector, right? If it is drawn from A to BC, then AB by AC will be equal to BD by DC. This is extremely important from an angle bisector standpoint. AB, so like from wherever you draw the angle bisector, so AB by AC will be equal to BD by DC. Similarly, if we write the theorem for this angle bisector, like for BE, let's say, so then the same theorem will get written as the two sides that are joining. So AB by BC will be equal to AE by EC. Will also hold true if B is the angle bisector. Right. So this is the angle bisector theorem. The other property or formula you can say is that okay, you might have a question, okay, like we know the angle bisector proportions, like what it divides into, but what is the length of this angle bisector, right? So the length of angle bisectors can be found using this. AD square, for example, for angle bisector AD will be equal to AB into AC minus BD into DC. This is the length of angle bisector. Like basically you have to calculate this and then they take the square root. This is the angle bisector. Right. Similarly, if we want to write it for BE, so just the same procedure. So BE square will be take the sides that are joining at this. So basically AB into BC minus A into EC. This is the sort of the formula for the length of the angle bisector. Okay. So, and we'll do questions like combining some of these concepts as well. But yeah, from a conceptual standpoint, this is how it is. Okay. Now coming to the next important center of the triangle, we'll now look at medians, which is a big topic in itself. So we look at basically centroid, and centroid is the meeting point of medians. Medians are nothing but in a triangle, like you draw a line to the midpoint of a side, that is called a median. So this will be a median on side BC. So AD will be the median. And median meaning it will bisect BC, so BD will be equal to DC. That is a median. And again, if you draw all three of them, then the meeting point would be called as the centroid. So if this centroid is typically represented by the letter G, so that's the meeting point of median, right? And when it meets, right, so the ratio in which it divides is basically 2:1. This is a very popular ratio. So 2:1 is the ratio in which the centroid divides the medians. So for example, AG will be equal to 2/3 of AD. Similarly, BG will be equal to 2/3 of BE if this was E. Similarly for CF. Essentially, like wherever is the source of the median, right? Wherever it's sort of starting from that vertex, that section is 2/3 of the total median. That's why the ratio 2:1. Similarly, you could have asked that, okay, like we know the ratio for medians, but if this was angle bisectors, as we just discussed, what would be the ratio for angle bisectors, right? So actually should have covered it there itself, but yeah, let's just cover it now. So if you have angle bisectors meeting at a point here, which is the in center as we discussed, so you can ask that, okay, like what is the ratio of, let's say, AI to ID, right? So the ratio of AI to ID is AB plus AC upon BC. So like wherever you're drawing the angle bisector from, the two sides that are linked to that, those get added, and the third side comes in the denominator. Like if we have a BE angle bisector, so then basically the BI by IE would be equal to AB plus BC over AC. Why? Again, B is the source, so AB plus BC upon the third side, which is AC. So this is the ratio in which the incenter divides the angle bisector. This is the ratio in which centroid divides the median. This is a more popular ratio. Like you will find this used at many more places than you will find this. But this is a good to know ratio as well. It will save you a lot of time in some problems, because typically people don't know this division ratio. Like most of the people that I've come across have typically know the 2:1, but like are not very familiar with this. So useful stuff. So this is the median. Now the third and the very important property, like there we had the angle bisector rule. Here the important formula is the Apollonius theorem, which is around the length of the median. So if you have here, and this is the median, so A, B, C, D, and so what is the length? For the length of AD, if we are asked to find, the rule goes that AB square plus AC square equal to 2 times AD square plus BD square. AD is the median. So if you know the sides, you can find the median through this formula. This is very important, called the Apollonius rule. Like the name is not important, but just for reference. Right. And again, we know that BC square is nothing but BD square is nothing but BC by 2 the whole square, because BD is equal to CD. This is the midpoint, right? That's the definition of the median we just discussed. So BD square will be BC square by 4, because BD is BC by 2. Somebody had a question, it seems. Please go ahead.
Sir, actually due to net issue, I went off. So can you explain the second part, that is AI by ID?
Sure. Yeah. So like right here we have the 2:1 ratio, right? That the centroid divides the median in 2:1. So like it's a similar ratio for the angle bisector case. So like the AI by ID, the I is the incenter, will be AB plus AC by BC. So basically wherever you're drawing the angle bisector from, the root vertex sort of, the sides that are joining up to it come in the numerator and the third side comes in the denominator. So AI by ID is AB plus AC by BC. Similarly, for example, if we write it for this, then BI by IE will be, it is originating from B. So it will be AB, this one, plus BC upon the third side, which is AC. Make sense?
Okay. Okay.
Okay. So this is the Apollonius rule for finding the length of the median, right? Now, the fourth thing is if you join all the, like if you basically make all the three medians in a triangle, this one, this one, this one, and again medians, this is equal to this, this is equal to this, this is equal to this. So basically this will be the centroid, and this joining all the three medians basically divides the entire triangle into 6 equal halves, right? So basically if you count these, this is 1, 2, 3, 4, 5 and 6. So these 6 are equal parts, and the reason this is important is that especially in questions regarding area and stuff, right? If you have all the three medians, you can just calculate the area of one of these triangles, multiply it by 6 and get the total. So that is where like it kind of finds its application. So this is the median. Okay, and in terms of coordinate geometry, if you have a, like if A was, let's say x1, y1, and we'll discuss coordinate probably tomorrow, but like this is since it's covering this, so makes sense to cover it. So the centroid would be x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3. Simple, no rocket science, just summing up the three vertices and dividing by 3, summing up the three vertices, dividing by 3. So this is the centroid coordinates. The in-center coordinates would have been, if you have to find out the in-center from like x1, y1 and x2, y2 and x3, y3, then the in-center coordinates would be ax1 plus bx2, and I'll just revise the diagram as well after writing this, plus cx3 by a plus b plus c, and ay1 plus by2 plus cy3 upon a plus b plus c. So again, if you sort of get the drift of this, then the y coordinate comes automatically. So this is the coordinate of the centroid, this is the coordinate of the in-center, and the figure for like basically if, yeah, here essentially if this was x1, y1, this was x2, y2, this was x3, y3, small a would be the side opposite the vertex A. So this would be small a, this would be small b, and this would be small c. So essentially a into x1, so basically bc into x1 plus b into x2, which is basically ac into x2 and c into x3, etc. So like these notations will remain consistent, right? So throughout this session basically, so small a will always be the same. So this is the formula for the coordinates of the in-center if you're given the three coordinates of the three vertices, and this is the formula for coordinates of the centroid. Okay, cool. With that done, let's just go to the next one. The next important point would be the orthocenter. Orthocenter is nothing but, again, let's start with the definitions. Meeting point of altitudes. Altitudes is nothing but perpendicular. You draw 90 degrees to all the three sides. This is these three are the altitudes, and the meeting point is the orthocenter. Typically, it's denoted by H in general geometry, but yeah, I mean, it does not matter really, right? So, but just for convention purposes, this is the one. So A, B, C. This is the meeting point of altitudes. And orthocenter, the how it is different from the other points, like obviously except the definition, is that it lies on different places at in different cases. If it's an acute triangle, like all angles are lesser than 90, then the orthocenter lies inside the triangle, like in this case. If it is a right triangle, the orthocenter lies at the 90-degree vertex. So if it was this, then this is the orthocenter. If it's an obtuse triangle, like let's say this or something like this, right? Then the orthocenter lies outside the triangle. So really, if you think about it, the orthocenter is inside the triangle only for an acute triangle. If it's an obtuse, it will be outside. If it is a right triangle, it will be on the 90-degree vertex. So that's one thing. The second thing is regarding the orthocenter, right? So let's, like, it's very direct, right? Like the 90 degrees, the meeting point is the orthocenter. Let's study some of the properties of altitudes while we are discussing them, right? So let's just draw a new figure for reference side. If this is H, right, the first property that we need to know is the ratio of the altitudes is inverse to the ratio of the sides, right? Like I'll just write it down so that it's clearer. So like AD, basically if the ratio of altitude is given as, let's say, 2:3:4, the sides ratio will be 1/2:1/3:1/4. Okay, and it works the reverse way as well. If the sides are given as 3, 4, 5, for example, or like any three sides of a triangle, then the altitudes will be in the ratio 1/3, 1/4, and 1/5. Okay, so like this is one property that you should know. You might have seen questions asking like, okay, if these are the two altitudes of a triangle, what are the possible values for a third altitude, etc. So those questions are based on this property. We'll come to those questions as well. There's a specific question on this specific property. We'll come to that. But yeah, it's a good property to remember. The third is, let's say if this is H, right? The third property is that, okay, let's just write this way. HD by AD, which is the small by big, plus HF by FC plus HE by BE equal to 1. So small by big plus small by big plus small by big is equal to 1. Right. So HD by AD, HF is this, by FC and HE by BE will be equal to 1. So in case you know some of these proportions, you can find the other ones as well. Right. And to the question of, okay, how does this link to any other concept that we have studied? Yes, it does. So if you have the three altitudes, let's say A1, A2, and A3, then 1 by A1 plus 1 by A2 plus 1 by A3 will be equal to 1 by small r, which is the in radius. This is extremely important. The sum of the reciprocals of the three altitudes will be the reciprocal of the in radius. This is how you can, so they might like this basically, for example, like the, altitudes, they might give two, you might be able to figure out the third one and figure out the in radius in a much shorter, much shorter duration. Otherwise, what you'll have to do is basically like use that altitude to get the area, then calculate the semi-perimeter and get the in radius by A upon S. But this is sort of a quicker workaround to that. Okay, so this is the one. There is one sort of a special case, like in general, which keeps popping up in this or that exams, which is basically there will be a right triangle and there'll be a 90 degrees from this 90 degree. So there'll be an altitude from this 90 degree angle. Right, it's been asked like in very recent CATs as well. So whenever you have a right triangle and there's an altitude from the 90 degree, right, the one thing that you have to remember, and we can derive it obviously, but yeah, it is good to remember, is that BP square, like the length of this altitude, the square of that is equal to AP into PC. Is AP into PC. So it's sort of the product of the segments will be the square of this altitude. This is one. And the second and the last thing that you need to remember about this setup is that all the three triangles are similar. This is similar to this one, this small is similar to the large one, and this we can prove, right? Like this is 90 degree and this is common. So for example, if we take this triangle, so triangle BPC, and if we take triangle ABC, so C is obviously common, so that is there, and one it is 90 here, and this the big triangle is 90 here. So two angles are same. So by AA similarity rule, those will be similar. So again, this is also a decent result to keep in mind. And yeah, so because like whenever you have similarity, then you can kind of get the side ratios from that and find out any missing sides. And this setup has come like multiple times in different exams. So it makes sense to just make a note of it. Really, right? So, and in fact, actually, now that we have discussed the similarity bit of, right, so basically let's just write it down properly. So triangle BPC, which is the smaller triangle, what will it be similar to? In similarity, we'll discuss similarity also as a topic. But in similarity, the most important rule, everybody knows SAS, AA, AAA rules, etc. Everybody knows that the most important thing in similarity is to name the triangles correctly. So if it is BPC here, so the first triangle you can write any way you want, but the second triangle has to be written as per that. So for example, in the first triangle, you have BPC. C is still common in the second triangle. So C will come in place of C. So that's C and C match. In place of P. So P was 90 here. So you will have to write the 90 here. That is angle B. And this will then be the remaining one, which is A. So again, just to reiterate, the C matches with the C here because it's common. The P was 90 here. So we have to write the angle that was 90 in the other circle, which is B. And the A is the remaining vertex, so A matches. So if we write the side ratios from this, right? So like the three side ratios would be BP over AB, the first two from this, etc. Right? And PC by BC is equal to BC by AC. Right? So these are three side ratios, and again, if you sort of start combining these, and again, you may be given some of the sides, and you can easily figure out the other sides from this equivalence as such. Like for example, from the last two, right? Using these two, you can conclude that BC square equal to AC into PC. So for example, if you were given two of these, you could find out the third one. Like general similarity principle that you apply, right? This is how you would have worked out. Like you would have solved similarity in general as well for the unknown side. So this is one other concept here. Okay. Now, any doubts up to this point? Or any property is not clear? Hello? Yeah.
Yeah. For the last property that you told, if this triangle is isosceles size triangle,
yeah,
then the triangle APB and BPC will be similar, right?
No, it will always be similar.
I was not able to figure it out.
Sure. So, okay, let's just, for example, like your case specifically, let's just draw it out. So you're saying that an isosceles right triangle, right?
Yes.
Here. So this is then 45, and basically we are drawing a perpendicular here. So let's have the same naming convention as that. Now this is 45 for an isosceles triangle, and this will also be 45. This toe is actually even more similar because like here everything is equal. So like for the small triangle, if you see, so we are comparing this small triangle to the whole big triangle. So if you're able to find two angles that are same, it means they are similar. So in this small triangle and the big triangle, C is common itself. And also one angle here is 90, and in the big triangle here the angle is 90. So they will still be similar, right? So let me just write it down. Angle C is equal to angle C from the small triangle, from the big triangle. Also in the small triangle, the angle BPC is 90, which is equal to the angle ABC in the big triangle. So if two angles are equal, the third angle itself is equal, so the triangle is similar.
No, actually I was saying that if it is not the isosceles right angle triangle, then will APB be similar to BPC?
Yes. Because the angle C will still be common, right?
Okay.
Let's make it 30. Let's not make it isosceles. Let's make it 30, 60, 90. Right. Still, this angle is common, right? Irrespective of what this value is, it will be a common angle across the small circle and the big circle. So it will always be similar, irrespective of what the nature of the triangle is. And in fact, all three combinations will be similar. Like this triangle is similar to this triangle, this triangle is similar to the big one, and this triangle is similar to the big one. So, but yes, once again, it's important to sort of name the triangles correctly once you're, writing it those similarity relations. The first triangle you can name anyhow, but the second triangle has to be named as per that then.
Okay.
Okay. Now there is just one more center, like in terms of the prominent center, which is the circumcenter, and this like does not have too many properties as such. This is the meeting point of perpendicular bisectors. So perpendicular bisectors would be 90 degree and cutting these sides equally. If you draw all three of them, the meeting point would be circumcenter. But this definition, okay, it's important from a theoretical definition standpoint, but the main definition of the circumcenter is that if you draw a circle here which touches all the three vertices, like it touches A, B, and C, the center of this circle is called the circumcenter. So this point is the circumcenter. Typically it's denoted by O, but okay, whatever. Okay, so this is the circumcenter. So whenever you draw a circle and the radius of this circle, like basically this length would be capital R, this would be capital R, this would be capital R. So this is the radius of this circle, this is R, this is R. So the more important definition, okay, it's a meeting point of perpendicular bisectors, yes, but the more important definition is that if a circle passes through the three vertices, the radius of that circle is called the circumradius, and the center of that circle is called the circumcenter. Right. So this is also important from two or three other relations that we have. Like for example, the area of a triangle whenever we need to find out, right? So the area of a triangle would be equal to A into B into C upon 4 times capital R, where A, B, C are sides of the triangle. Once again, as we had discussed, right? So the notation, so this is A, B, C. So this would be small a, this would be small b, this would be small c. So area of a triangle would be ABC by 4R, or you can say that if you have to calculate the circumradius, so this would be integration ABC by 4 into A, where A is the area. Right. So this is one relation that is important. There are other important relations for the circumcenter as well. But another property that you need to remember for circumcenter is that similar to the orthocenter, right? For an acute angle triangle, the circumcenter lies inside. Like for this one, this is an acute triangle, so the circumcenter lies inside. For a right angle triangle, the circumcenter would be the midpoint of the hypotenuse. So this is the hypotenuse. The midpoint of this would be the circumcenter. If this was, for example, ABC, and you drew a circle touching ABC, like something like this, then this would be the center of that circle. So clearly this is the center, and center as in the midpoint of hypotenuse here. So for example, if this is A, this or not A, actually A should, or actually yeah, this would be, let's say P, this would be P, then this would also be P, because this is the radius. So which is very important because like in problems you should be able to identify, like if it's a right triangle, the midpoint of the hypotenuse denotes the circumcenter, and all these three distances from it will be equal. These two will obviously be equal because by definition it's a midpoint, and also these will be similar, like this also will be P, because again this, like all of these are radius. So you can join basically any point and this would be P because all of it is radius. For an obtuse angle triangle, again the circumcenter lies outside the triangle. So like if you have an obtuse angle triangle, the circumcenter would be outside, so there are no relations there as such for the circumcenter. Okay, so this is the circumcenter essentially, and we also discussed, like as you remember, right, in the sine rule also we discussed that A by sine A, B by sine B, C by sine C equal to 2R. That R is this one, the circumcenter. Okay, so these sort of are the four major centers of the triangle, right? Now we should look at a few things here, that okay, how are these related, sort of, right? Okay, these are four distinct points, right? So if you have a triangle here, a general triangle, not talking about specific case of an equilateral or an isosceles or something, just a general triangle if you have, it's important to know that there's an abbreviation actually which you may, if you can remember, it will be good. It's called HGO. H is the orthocenter, G is the centroid, and O is the circumcenter. HGO. What this abbreviation means that these 3 points will always be collinear, will lie in a straight line. So for example, there's a line here. So H will be somewhere here, G will be somewhere here, O will be somewhere here. And this is always true for all circles. So these 3 points are always collinear in a straight line. This line is called the Euler line. Again, it's not important to know the name of the line, but it's important to know that these points are collinear. H, G, and O. Again, if you would notice that there is no in-center in this relation, right? So the in-center may or may not be collinear. It is collinear in the case of isosceles and equilateral, but not in case of other triangles. So it would lie somewhere different, like let's say here or here somewhere, typically, unless it's an isosceles triangle wherein it would lie only in the same line. In equilateral, all these are the same points. So equilateral is like the simplest, like the most, easy to handle case sort of. But in every other triangle, these would fall in a straight line, collinearity. And the important relation why we need to study this is because there's a relation which says that HG will be equal to twice of OG. So this distance will be twice of this distance. They may give you the distance between G and O. Again, let's just address them by their proper names. So basically this says that distance from ortho to centroid will be equal to twice of distance from centroid to circum. Okay, so they may give you one of these distances, you may be asked to find the other one. Right, and they usually don't like make it complex in general. So, but it's important to remember the distance, that these distances have a relation between them. Okay, so but if you see that there is no in center here once again, right? Now, the relation which is with respect to the in center here. So again, obviously, like if it is 2:1, right? So basically, if I give you one of these distances, all the other distances can be figured out. If I give you OH, then you can figure out this distance will be 2/3 of this. So basically, if we write it down, the HG will be 2/3 of OH. OG will be 1/3 of OH, essentially, right? That is the 2:1 rule. So if you know any of the distances, the other distances can be figured out. Let's say if you know OG and you need OH, you can figure that out. It will be just the 3 times of this. If you know this one, this can be figured out, and you need to know just one distance and everything else will be figured out here. Right. Generally, whenever they have asked this in like entrance exams, they have given the distance, like one of the distances, and asked you to find the other two. And again, they might also ask this in terms of coordinate geometry. You know the distance formula, right? So they might give you like, okay, if this is the coordinates of the orthocenter, this is the coordinate of the centroid, what is the coordinate of the circumcenter? Or they'll give you 2 of them, they'll ask you to find the third one. So again, the same thing, just use distance formula, and actually you can eliminate options. You don't even need to calculate that. Whichever option by the distance formula obeys this rule, that will be the correct answer. Okay, so like in that they had asked that, if this is the coordinate, this is the coordinate, then what will be the possible coordinate of O or something, of O or H, and they're given the other 2. So that should be straightforward. You just have to test the options with the distance formula and see which matches here. So that should be it here. Okay, now just for reference, right, and you don't need to remember it, but just for reference, this distance in general, the orthocenter and the circumcenter, the total distance OH from a formula standpoint is given by 9r square minus a square plus b square plus c square. You can make a note of this. They generally don't ask, but yeah, just from again a completion standpoint, they'll typically readily give the distances or like readily like tell you some of the values and ask you to find. But if they don't, this is like an SOS formula that you can use. 9 capital R square minus a square plus b square plus c square. The root of that would be OH, this distance, and once you get this, the others can be figured out. Again, coming back to the point of in center not being present in these relations, right? The relation and the more frequent relation that is used for in center here is distance between in center and circumcenter. And this is actually much more common. In center and circumcenter, the distance is given by r into r minus 2 small r, the root over. Again, no need to remember formulas as such. This relation you need to remember, and this formula, yes, you need to keep in mind because it will save you some time. Capital R into R minus 2R, and this is much more useful than this one. This people won't ask typically. This is like just an emergency kit sort of for this thing. In center and circumcenter distance has been asked. So that's why root of capital R into R minus 2R. There used to be a fun question I used to share on some of the group sites. So it said that if for a triangle the capital R or the circumradius, capital R is always circumradius in geometry, small r is always in radius. If capital R is, let's say 10 and in radius is 6, what is the area of the triangle? And people used to give answers but didn't realize that this triangle is not possible, because for triangle to exist R has to be greater than or equal to 2 times small r. But okay, this is just for a fun trivia, but in general this formula is important to keep in mind. Any questions to this point?
Yes, sir.
Sure.
Sir, in center formula, ABC by 4A, is it valid for all the geometrical figures?
No, this is valid only for triangles. So
Okay.
if you try to like extrapolate this to say that okay, for a quadrilateral I'll have ABCD by 4A, it won't work.
Okay, sir. The second thing is this HGO thing which you mentioned.
Yeah.
Is it valid for every triangles?
Yeah. So the thing is that it is valid for every triangle, yes. The only thing is that for equilateral, let's say, like these points are same. H, G, and O are the same point. So this like doesn't hold relevance for equilateral triangle, but yes, for every triangle this is valid.
Okay, sir. Thank you.
Okay. So now we come to the special cases of the equilateral triangle, which is sort of the most beautiful figure in geometry because it's the simplest. So equilateral triangle is 60-60 each angle, like everybody would be knowing that obviously, but yes, the important thing is that for equilateral all 4 points are the same. So this point will be H, G, O, I. All points will be the same point. So like in center, circumcenter, centroid, orthocenter. All points are the same point. To say that basically that okay, if you like whatever definitions we have discussed, right? So all of them relate to the same point here. For example, for in center, we saw that okay, this is the in center. Now for an equilateral triangle, the same point will be circumcenter. So for example, if you draw a circle here, it is circumcircle. So the same point will be the center of both this circle and the big circle, because it's both the in center and the circumcenter. Similarly, if you draw the medians, they will meet at this point itself. In the same point, this one. This will be a centroid as well. If you draw perpendiculars, it will again meet at the same point. It's the orthocenter as well. So the most simplistic construction that is possible is the equilateral triangle. Right. Now talking about the equilateral triangle, right? So there are a few formulas here which we derive and sort of avoid memorizing as such. The area obviously is very common, root 3 by 4a square. So that is like every side is a. So this is like everybody knows, root 3 by 4a square. Now, what is the circumradius and the int radius for this? It's always good to keep that in mind, but we'll also derive this just so that if you're confused or you know you're sort of not able to recall, then you can easily derive it in one line. We know that area of a triangle, which is this one, is equal to ABC by 4R from the previous slide, right? So area is this much, and ABC here will be A cube because B and C are both equal to A as well, and divided by 4 into R. So 4 gets cancelled, and A becomes, or R becomes A upon root 3, which is the circumradius of an equilateral triangle. Easy to write, just using ABC upon 4R, and the circumradius is A upon root 3. Let's talk about the end radius now. We know that end radius is area upon semi-perimeter. Area is root 3 by 4A square. Semi-perimeter here would be A plus B plus C by 2, but A plus B plus C would be 3 times A because it's an equilateral triangle, so it will be 3A by 2. And this actually gives you A upon 2 root 3. So for any equilateral triangle, the circumradius would be A upon root 3, the end radius would be A upon 2 root 3. So like to say that, okay, end radius is half of the circumradius, essentially. So basically, if you draw, like if you see from this standpoint, then this radius would be half of, let's say, this capital R. So this would be A by 2 root 3, this would be A by root 3. The other relations still hold, like the 2:1, etc. Like again, this point it will divide this line into 2:1, etc. Because again, this point you can treat it as median, center, and center, center, whatever. So this is one. These are the two relations that you should know. For also for equilateral triangle, right? Equilateral triangle is beautifully symmetric in other ways as well. For example, in an equilateral triangle, there are some interesting relations that kind of make it simple to operate. Yeah. If there is any point, okay, let's first talk about the height of an equilateral triangle. Right? If you talk about the height of this, you can find the height of this. This will be, the height is the same as median, because for an equilateral triangle, the altitude is the median, is the angle bisector, is everything. So altitude will be the same as median, will be the same as angle bisector, and everything, right? So height you can find out. This is A, this is A by 2. So height of an equilateral triangle will be A root 3 by 2, direct Pythagoras in this triangle. Right, and so this is the height. The application of the height is, if you take any random point in a equilateral triangle, let's say this point P, right, and you draw perpendiculars, like you measure the distance of P from the sides. Like this is a perpendicular, this is a perpendicular, this is a perpendicular, let's say PM, TN, and distance in geometry will always mean like a perpendicular distance, right? So if we say that, okay, from this point, this, how far is this point from this line? So you will draw a perpendicular in general. So if you want, if this is an equilateral triangle and if there's an internal point P and you sort of measure its distances from the side, the perpendicular distances, the sum of these perpendicular distances, PM plus PN plus PT, will always be equal to the height of the triangle, which is A root 3 by 2. The name or the theorem is not important, that's why I'm not naming it, but yeah, just in general. So like if they ask like, okay, there's an equilateral triangle and like line segments are drawn from an internal point to the sides, or maybe like there's a person inside this equilateral triangle. So how, what is the sum of his distances from this side, this side, this side, etc. Something of this sort. So the sum of those distances, irrespective of wherever the point P is, if it was P here as well, then the sum of the distances like this plus this plus this perpendicular distances would have been equal to A root 3 by 2, which is equal to the height basically. So that is there. That's one relation. Okay. And
Hello.
hello, yeah, please.
Yeah. All these sides are perpendicular to the point P.
This
Like
distance,
PM.
the distances, yeah, the PM will perpendicular. Like whenever in geometry we say, even if it's a general triangle, right? So if let's say somebody asks you that, okay, how far is point M from side AB? Right, the answer will always be the perpendicular distance from M to AB. Like it's not like you can draw any line from M to AB and then call this call this the distance of the point from the line.
Okay.
So this perpendicular distance gives you this relation.
Okay.
So that is it. From an equilateral triangle standpoint, you can also have a relation from like how far are these from the vertices. So for example, like this was with respect to size, right? If you have an equilateral triangle, let's say this one, and you any random point, let's say P, and you draw, like you connect this P to the three vertices, the sum of these three distances will be equal to A root 3, is half of this basically. So like let's say you have the point P here, you join it to the three vertices, mark it as X, Y, Z, So the x, y, z, like the lines to 3 vertices, will sum up to a into root 3. So this will be equal to the height, and this will be equal to a root 3. Make sense? This is
Sir?
actually not necessary. Like this is like as in okay, this is necessary. It will always hold true, but in general, this is not asked like in question. This like is comes of use at some point. Yeah, sorry. Please go ahead.
Yeah, sir. So PN, PTN. So these are all the three different altitudes we can say.
Not altitudes per se, because like altitudes are when you draw something from a vertex of the triangle. So like AD would be an altitude, and this one. This is from an internal point the perpendiculars. By definition, like altitudes would have to be from a vertex. This is from any point inside the triangle.
Okay, sir.
So this you actually did not even keep in mind, but this may suddenly be of use at some point. So this is the stuff for an equilateral triangle, right? Now coming to the other special case, which is the right triangle. Right. So as we covered that the midpoint of the hypotenuse will be the circumcenter of this. So to say that, okay, if let's say this is A, B, C, so this is basically A, this is basically B, this is basically C. So this will be B by 2, B by 2, and this is the circumcenter. We just covered this, right? Similarly, this would also be B by 2 because circumcenter is equidistant from the vertices, right? So if you draw a triangle, basically this will be the radius of that circle. So this is the first important point in terms of the centers around the right triangle, and this was the orthocenter as we mentioned, right? That the vertex of the right of the 90 degree is the orthocenter in case of a right triangle. The other relation in terms of a right triangle is that the in radius of a right triangle is a plus b minus c by 2. Actually, let me just redraw this figure once to align it to the convention. So this is right triangle, let's say. So this is with respect to this. So this would be A, this would be B, and this is C, the hypotenuse. So for this triangle, the in radius would be A plus B minus C whole upon 2, which is the legs of the triangle minus the hypotenuse whole half will give you the in radius. And we know that the circumcenter is the midpoint of the hypotenuse. So the circumradius, capital R, would be C upon 2. Right? So the circumradius, as in if you draw a circle, then the radius would be that one. So it is the half of the hypotenuse C upon 2, and R is this. This is always true for a right triangle. Right. So basically, if you add both of these, you will get R plus R equal to A plus B by 2. So sum of the in radius and the circumradius is half of the sum of the legs of the right triangle. Okay. So this is one relation. The other relation is that for a right triangle, the area is equal to R into small r plus 2 times capital R. This is important. Actually, all these relations are sort of important only. So yeah, this, okay, still you can derive from the above two, so not really to remember anything here, but this needs to be remembered. This is anyway the sort of a definition itself, so like this anyway needs to be kept in mind. But yeah, the area, like it can directly come of use, that okay, this is the in center, this is circumcenter, what will be the area of the triangle? So you can say that small r into small r plus 2 times capital R. For example, if the incenter is given as 8, the circumradius is given as, let's say, 20. So the area would be 8 into 8 plus 28. 8, sorry, 8 plus 40. 8 into 48, whatever this is. So this is regarding the right triangle. And again, we just discussed also, right, that in a right triangle, if a perpendicular is drawn from the right angle itself, then we just saw that let's say this is P. So CP square equal to AP into BP. This into this will be equal to CB. So this basically sort of encapsulates what is important from a right triangle standpoint. Okay. So yeah, now let's move on to some other basic properties of triangles, right? So, and deliberately, I was discussing this because sort of it's easier to do it early in the session because it helps to ensure that level of focus as well in the beginning. Now, coming to the concept of the area of a triangle, now there are many formulas around this. Let's just list them down. First is half base into height, really like the school years formula, right? Nothing much going on here. Base height, half base height, done. Second is half AB sine A or half BC sine, half AB sine C or half BC sine A, or half AC sine B. Again, this refers to our standard diagrams of A, B, and C. Half AB sine C would be around this, BC sine A around this, sine B around this. Right, and so all these three represent the areas. The third, the famous one again is the Heron's formula, which is square root of S minus A, S minus B, S minus C. S is A plus B plus C by 2. Fourth is using the in radius as we again discussed, which is area equal to in radius as in R into S, where R is in radius, S is semi-perimeter. Very important. The fifth, as we saw that for a right triangle, the area was R into R plus 2R. Right. Now, all these are expressions depending on what parameters you have available. Again, of course, there was another one. Let's just write it for thing. ABC where 4R is also area. R is circumradius. So there are like half a dozen formulas for area. And like if you're given coordinates, there's a separate formula for coordinate geometry as well. But the point is that whatever parameters you have available, you have to use a certain area formula to sort of get the area based on those parameters. So for example, if you're given the in-center, you need to look at this one. If you're given the angles, etc. and all, then these ones will be there. But actually the simplest formula of all this, the half base into height, has a certain nuance to it. Let's just discuss that and how it can be used powerfully actually. Right. So for example, if you have a triangle here, let's say, right, or actually both this and this have, like, these two seem to be the simplest formulas, but there is a nuance to it, which is this one. So for example, if you have a triangle ABC and you have a point D, now there are two triangles here, like ADB and ADC, right? For example, if the base lengths are in a ratio A is to B, right? So for example, BD is to DC is A is to B. Then the area of these triangles will also be in the ratio of A is to B. So triangle ABD by triangle ADC, will the areas of them will also be in the ratio of A:B. Why and how? See, what is the area of triangle ABD? And again, understanding it is always safer, just in case you're not able to recall. So the area of ABD will be half A into AD sine. Okay, let's write it on a note page itself. Getting that in there. Right, so let's just draw it again. Let's say here. So if this is, let's say, x and y, the ratio, so BD by DC equal to x and y. So the result is that the area of triangle ABD over triangle ADC will also be x and x by y. How? What is the area of triangle ABD? It will be half into BD into AD into sine of this angle, BD, AD, and the sine of the included angle. So let's say this angle is theta, so sine theta. And what is the area of triangle ADC? Half CD into AD. AD is common in both triangles, so AD features in both. Sine of, what is the angle here? This is 180 minus theta, and this is what we have to take. We know that sine theta and sine 180 minus theta are the same thing. So when you divide these to find the ratio, these get cancelled out, AD gets cancelled out, half gets cancelled out, and you're remaining with BD upon CD, which is the same ratio. So this is how you get the result, but it's a very powerful result that the ratio of areas of two triangles will be the same as ratio of their bases. We'll look at a couple of questions when we get to the questions as well for this. Right, so for example, if this is 3:4, then the ratio of this area by this area will also be 3:4. This is like from a naming perspective, it's called the base area theorem or the base area ratio rule. So this is important. Okay, so in terms of area, the only other thing is that for an equilateral, we saw that the area, let me just write it again, is √3/4a square. For an isosceles triangle, again, all like you can always find the area by Heron's, right? But sometimes that gets a bit calculative. If you're given the sides, for example, if an isosceles triangle, if this is 3, 3, and 4, for example, right? You can always apply Heron's to get the area if the sides are given. But whenever you see that it's isosceles, it's always good to sort of have this shorter formula, which is the formula is b/4 √4a square minus b square. This helps to calculate it very quickly. B is the different side and A is the same side. So in this figure, A will be 3 with the same side and B would be 4. So the area here would be 4/4 √4 into A square, so 4 into 3 square, 4 into 9, 36, minus B square, so minus 16, so which is √20 or 2√5. So it's a much quicker way than Heron's will also give you the same answer, but just to save time, this is the formula for an isosceles triangle: b/4 √4a square minus b square. Okay. So now that we've covered this, right, let's move on to the next bit in this, which is, and again, like please feel free to ask any question or stop me at any point if you feel that something's not clear. The next topic is similarity. Pretty sure you would have all studied this, and it's just basically that there are two rules to keep in mind here. So if any two angles are similar, so if this is theta, this is alpha, this is alpha. those triangles are said to be similar by double A rule. And the naming is important because that will dictate how you put that equation for the sides. So in this case, for example, ABC is similar to what triangle? So A we cannot comment because we don't know like what angle A is equal to here. B we know alpha is same as alpha. So in place of B we'll write R. The B was in the middle, R will be in the middle. C is theta, which is P. So in place of C there will be P and the remaining one would be Q. So these two will be similar. So if you had to write the side ratios or in order to find the sides, it will be AB by QR, the first two of this, equal to BC by RP, last two, the first and a third. And this you can use to find unknown sides and stuff. So this is the AA rule or the triple A rule, because obviously if two are equal, the third will also be equal to that. The second is the SAS rule, which has a small detail to it. It's the same two figures essentially. Now, this basically says that if the side ratios match, then the triangles will be similar. So, for example, if we are given that AB by PQ is same as AC by PR, and this, like, if we are given that this is true, and the included angle, please note the keyword here is the included angle. So for example, if the given ratio is with respect to sides AB, PQ and AC, PR, so the included angle would be this one and like PQ and PR, PQ, PR, so then this one. These two angles need to be equal, and which is very, very important. The word included angle is key here. Right. So for example, if you were given that, okay, this is theta and this is theta, and this ratio was true, would the triangle be similar? No. You need the included angle to be equal. This needs to be theta for the triangles to be similar. Yeah, so this needs to be theta. So the included angle needs to be equal. What do I mean by included angle? So the sides which ratios are given, like here the ratios are given as per AB and AC of this triangle, AB and AC, or PQ and PR of this triangle. The angle that is contained between them, those need to be equal. Then only you can say triangles are similar. So it's always a good check to see that what sides are proportional. Right. So this is similarity. Again, if the triangles are similar, like, okay, this is sort of to like gauge whether two triangles are similar or not. If they are similar, then the sides are in the same ratio. So for example, if two triangles are similar, then AB by PQ will be equal to AC by PR will be equal to BC by QR in that ratio. Right. And they will, like, so if this is like 1:2, if this is given 1:3, then this would also be in the ratio 1:3. So if this is 2, this will be 6. If this is 4, this will be 12, and so on and so forth. Right. So that is the one. The ratio of areas would be the square of the ratio of sides. So here the ratio of side was 1:3. The ratio of areas would be 1:9. The ratio of areas is always 1:to side the whole square, like the ratio of side square. Okay, so for example, if the sides were in the ratio 3:4, the areas would be in the ratio 9:16. That's just it. And this would come of use actually. And so this is the, like, this is with respect to what the impact of similarity would be. Right. Now, how do we, like, okay, if somebody tells you or asks you that, okay, are these two triangles similar? You would be able to easily gauge, right? You will compare the angles. Okay, even if the angles are not equal, you will compare the proportion of the sides and then see that, okay, if there is some proportionality, the triangles would be similar, and if the included angle is equal. Okay, but in questions, how do we know that similarity has to be applied? Right. Okay, before we get to that, there's one small nuance that needs to be mentioned here. Again, something that people remember from similarity is that the ratio of sides is same. So this by this, or something like the ratio of sides would be 1:3 for all the pairs of sides. The people remember that. People remember the ratio of areas. What people do not remember generally is that if the two triangles are similar, then the ratio of sides will be the same as ratio of heights So heights will also be in the same ratio, will be the same as ratio of in radiuses. Like all the parameters that we studied, right, those will be in the same ratio, will be equal to ratio of circumradiuses. So two triangles are similar. So side ratios obviously like people would realize it's the same, but that the even the height ratio, the in radius ratio and the circumradius ratio will also be the same. Right. So if this is like 1:3 in this case, or let's say if the side ratio is 3:4, the ratio of in radius of those triangles will also be 3:4. The ratio of circumradius will also be 3:4. Only the ratio of area would be the square. Okay. So now coming back to the point of how do we know that in a particular question should we start looking at similarity or not, right? Because typically questions obviously won't tell you, right? And this is the major catch in geometry as to how to strike questions faster, like how to sort of hit the nail. Yeah, please go ahead.
Sir, the ratio of orthocenter will also be equal to ratio of side, right? You have mentioned in radius and circumcenter in the last one.
Yeah. So you mean, so basically orthocenter is not a length, right? The length is the height. Orthocenter is the meeting point of the height.
Yeah.
So yeah. So basically height, that is why it's written here. So heights or altitudes, you can say that the ratio of heights or altitudes is the same as ratio of in radius, the same as ratio of circumradius. So all ratios will be the same. Okay. So now how to know where to apply similarity, right? What is the hints in the question? The first hint usually is parallel lines in the diagram. And this, like, if you have any setup with parallel lines, for example, you have this circle and this is parallel to this. PQ, BC. So basically, if this is parallel to this, then we know that this angle will be equal to this angle, corresponding angle, this angle will be equal to this angle. So these two triangles will be similar, the small and the big one. So triangle APQ will be similar to P is same as B, Q is same as C, so will be similar to ABC. Okay, so parallel lines, you should, like, whenever there's a figure, so you should start thinking in terms of, okay, like, if there's some relation from similarity that we can use. It's not mandatory that similarity will be used there, but similarity would definitely be one of the potential options to use in case the question asks for that. Right. In fact, you also have a theorem around this, like not a theorem per se, but just a result that if it's a triangle ABC and you have a line parallel to the base, and this is parallel to BC, so these two triangles will be similar as we've just discussed. This angle same, this angle same, common angle. Similar definitely. This whenever there is parallel line, there will be similar triangles. Right. Even if I extend this to another bigger triangle and say that okay, this is parallel to PQ, so basically it is MN parallel BC parallel PQ. So all the triangles will be similar. Like this will be similar to this one, this will be similar to big one, this will be similar to the big one. The ratios will vary, of course, but all the triangles will be similar. So any relation you can write and use depending on like what is asked in the question. So the result is that basically that if you join the midpoints of the two sides of a triangle, this one, so if you join the midpoint of two sides of a triangle, it is parallel to the third side and half of it. Right. So basically, if this is the midpoint of this is the midpoint of FM and N are the midpoints of AC and AB respectively, then MN will be half of AB. Only if it is a midpoint. And MN will be parallel to AB. Parallel to AB. So this is called the BPT or the basic proportionality theorem.
Sir.
Sure. Please go ahead.
Hello. Yeah. I mean, not necessarily every time if you connect the two midpoints of a sides, you will get a parallel line similar to third side.
No, it will always be necessary. If you are connecting the midpoint, they have to be midpoints. then see it will always be parallel, and if it is a midpoint, it will be half of the third side. So MN will be equal to half of AB, and MN will be parallel to AB. If you're joining the midpoints of, so for example, if you have a, let's say, and this will be true for all triangles. So for example, if you have this one, this, right, if you join the midpoint of these two sides, for example, this is the midpoint, it does not look like it, but let's say this is the midpoint of this side, this is the midpoint of this side, and then this line joining them will be parallel to the third side and is half of it. Maybe this would have been a better representation. Yeah, this is a better representation. Parallel to the third side and is half of it. And this will always be true. And any parallel line will create similar triangles. They don't even need to be midpoints. So for example, here it wasn't this line wasn't the midpoint, but parallel lines will always give similar triangles. Right, and this is the result for the basic proportionality theorem, that if the midpoints are joined, then the only additional thing is it would be half of the third side. So this is a midpoint, it would be half of the third side. Now what does this tell me? That okay, if this is half of this, then this will be half of this by similarity, and this will be half of this by similarity. So basically I know from BPT, basic proportionality theorem, that Mn is half of AB. So by similarity, Cm will be half of AC, Cn will be half of BC. Side ratios will be 1:2 in the small triangle and in the big triangle. So if side ratios are 1:2, what is the area ratio? 1:4. So basically this area over the whole total area is 1:4. How did I get to it? The side ratio was 1:2. There used to be they don't ask it nowadays, but there used to be this thing that okay, if you join all the midpoints in a triangle, all the three midpoints, what is the ratio of this area to this to like the overall area? Okay, so if we try to address this question, right? So we know that okay, and these are all midpoints. So BR equal to RC, CQ equal to AQ, BP equal to AB. These are all midpoints. And again, if these are midpoints, then by BPT I know that PQ will be half of BC, PR will be half of AC, and RQ will be half of AB. And also these will all be parallel to these sides. PQ will be parallel to BC, PR will be parallel to AC, and so on. So because they are parallel, once again, it means there will be similar triangles that are getting created. So this triangle APQ by ABC will be 1:4. As we just discussed, that if the side is half of the big triangle side, the area will be 1/4. Similarly, this triangle, the side triangle PBR, will be also be 1/4 of ABC, because even here the side ratio is this is half of this side is half of this again by BPT. So the area of this by area of this big triangle would be 1/4. Similarly, CQ will be half of not CQ, like this one, QR will be half of AB. So again, CQR will also be 1/4 ABC. So this will be 1/4 ABC, this will be 1/4 ABC, this will be 1/4 ABC. So the total they sum up to 3/4 of ABC, and so this again will be remaining, will be the 1/4 of ABC.
So this is true for all the triangles, right?
Yeah, this is true for all. You could have derived it directly as well. Like even if you take this triangle and the big triangle, even here the side, if you see this small triangle sides, so A side, this side is half of BC, this side is half of this side is half of this. So you know that the side ratios are 1:2, the area ratio is 1:4. So you don't even need to calculate the areas of these three individual, but just did it to illustrate this principle of this. But again, long story short, whenever you see parallel, that is a good indication that okay, it might be possible to apply similarity if the question requires something that needs similarity. Right? You will actually see these. You would have actually seen this some diagrams that are relevant here, right? So, for example, again, I know this section is for triangles, but even if let's say for circles we say, right? You would have seen figures like these here and joined here or something like this, right? Very common setup, really. So these are the centers of the circles. This is R, small r, this is capital R, or R1, R2, whatever. Right, and if you join here, again, since this is parallel to this, and how do I know this is parallel to this? Both are perpendicular, radius perpendicular tangent. So both are perpendicular, so this will be parallel to this. Again, this triangle will be similar to this triangle. If the rate, so and everything will be in the ratio of the sides then. So R by R will be equal to this. So basically, if I was to write an equation for this is P, this is Q, and this is R and R. So once I know that, okay, this parallel to this, these two triangles are similar, so all the sides will be proportional and in the ratio of R is to R. So if I'm given the ratio of radius, here is, let's say radius is 2, here radius is, let's say 5. So the side ratio is 2 by 5. Triangle APQ is similar to triangle AQC. This is similar to the whole triangle and the side ratio is 2 by 5. So which means that all the side ratios will be 2 by 5. So for example, if I write AB by AC will also be 2 by 5. This by whole is still 2 by 5. AP by AQ will also be 2 by 5. And similarly so on and so forth. Again, an application of similarity. Right. There's another this thing, and it used to be like not used to like basically there was a word problem around it that there is a like there is a straight wall or something or a ladder, whatever, and there are kept at two ends here and here. This is the ground. There are ropes tied to the top of this and rope. Not actually this one. Let me. Yeah, so one is connected to the foot of the next foot of the other. So for example, this is connected to the foot of this is connected to the foot of this. So they used to ask that, okay, how high above the ground is the meeting point of the two ropes? So what is this height essentially? Again, a similarity result that is used. And why similarity? Like it, or how do I know its similarity? Because again, this is parallel to this and these two are parallel to this. So once I know that they are parallel, right? So again, in this triangle, if we see this and the big triangle, so triangle this is DPD, similar to what? And again, just to reiterate once again, and cannot stress this enough, that the naming is of utmost importance here. So in this triangle BPD, I know that they are similar because like angles like created by parallel lines, like corresponding alternate angle, etc., would always be equal. But to name it carefully is the point here. So BPD and this big triangle, right? So obviously B and B is common. So where B is coming here, B will come here. Now P is 90 here. So we'll have to look at what is the 90 in the big triangle. So 90 is this. So in place of P, there will be A. And in place of D, whatever is remaining, there will be E. So let's say if this is this height is this height is Y. So this triangle is similar to this big triangle. To say that basically if we write BP by AB, like side ratios is equal to BD by BE is equal to PD by AE. Okay. So now again back to our question of okay, what will this height be essentially? So again, this height is PD, right? So we can write PD as H. Now we can use basically like for example we can use any, and similarly if these two triangles are similar, even these two triangles will be similar by the same logic, right? ADP and ABC, this one again parallel lines. Why? Because this is parallel to this is straight lines of, and this is parallel to this, so again the angles will be equal. This angle will be equal to this and this angle will be equal to this. So by double A rule, these angles will be similar. So triangle ACD similar to triangle ABC. So again, even from here, you will have the relation of PD by BC equal to, let's say, AP by AB. Right, and PD again is H basically, which we needed to find there, and BC again is Y basically. A here was X. So H by X from here is equal to BP by AB, and H by Y from here equal to AP by AB. And you can use this to sort of come up with a relation for H. So let's just continue it here. Basically, if we add these two, right, H by X plus H by Y will be BP by AB plus AP by AB. BP plus AP is nothing but AB itself, so this is equal to 1 actually, because BP plus AP is equal to AB, and AB by AB is 1. So H by X plus H by Y equal to 1. So basically you can derive H from here will be XY over X plus Y. So this is basically XY upon X plus Y. Again, no need to remember at all, but just to again show the application of similarity here. It's just a good example to sort of keep in mind. Right, so this is one application of like how to find similarity, because you will find these parallel lines cases coming up in several questions. The next hint of using similarity is if the question gives two angles as equals in the diagram. So if you, for example, have a random diagram, right, like this or something, and they give, let's say, this theta equal to this theta, then it should strike you that maybe similarity can be applied. Right. Again, obviously, one pair of angles more needs to be equal, or the side need to be proportional, but at least it can get you started on that line of thought. That okay, if angles are given as equals, can I prove them to be similar? So to prove them to be similar, you'll either have to prove another set of angles as equal, or you'll have to sort of like prove that the sides are proportional. Right. For example, if let's say, and this also used to be a common diagram, let's say you have a right triangle and you have a square, for example. This is a square inside a right triangle, right? And let's say you're given this, and you're asked the length of this entire AC, like what will be AC equal to, right? So how would we sort of go about this? We know that 3 and 4 is given, so this will be 5. So side of the square, and it's given that it's the square, so all sides are equal, and the vertices are at 90 degrees. So 5, 5, 5, 5, and this is 90, right? So now basically, if we see that if this is square, right? If we draw a line of this, and we need to find the length of this, right? So if we draw a line here, and this angle is given as 30 degrees, let's say, right? If we draw a perpendicular line here, right, and we call this angle as theta. So how much will be this angle? The sum of these three will be 180. This is 90. So this will be 90, and this is theta. So this will be 90 minus theta. So this is theta, this is 90, this is 90 minus theta. In this triangle again, this is theta. This is 90, this is theta, and this will be again 90 minus theta. So this again is 90 minus theta. So again, in these two triangles, essentially, I've proven that two angles are same. One is, this is 90, this is right triangle, and this is 90. So these two angles are equal. Also, this is theta and this is theta. So this also is equal. This angle and this angle is equal. So this is actually theta, not 90 minus theta. Let me just draw. Let me just basically put in the triangles of different diagrams. So this is theta, this is 3 and 4, and this triangle was, this is theta, this is 90. Right, so again, these two triangles are similar. Now, how do we name them? Let's say P and this is R. So triangle, and this is M, this is N. So AMP, in AMP, similar to triangle, how do we name this? M and R. So A is 90, so it has to match with the 90 here, which is N. M is theta, M has to match with the theta here, which is R. And the remaining will be M, which is this one. So to say that basically that AM by NR will be equal to AP by MN and will be equal to MP by RM. Right. Now we know that in this relation, again, the natural next step to this writing this relation is we have the equation now. So we can find sides. So where do we have maximum things given? Like here we know that the side of the square is 5. So MP we know is 5. MR we know is 5. Both are sides of the square. So this is 5, this is 5. So this ratio, all these ratios will be equal to 1. To say that basically AM will be equal to NR. Right. So AM equal to NR, AM we know is 3 here. So NR would be 3. We know 3, we know this is 30. We can find this length, and we can use AP equal to MN to find this. AP is 4, so this will also be 4. So we have 3, we have 4, and this we can find by using actually cos 30, which will be equal to CN by NR. Yeah, so this would be CN by 3. So CN is equal to 3 root 3. So the entire length of AC will be nothing but 3 plus 4 plus 3 root 3, 7 plus 3 root 3. If it was given that, okay, this is an isosceles right triangle, then you could have even found out the area, because isosceles area means that, okay, this side and this side will be equal. So you can just basically write half into AC square will be the area. AC you just derived. If it was given, then it was expressed. Otherwise, they'll give something if they want to find the area. But like again, this is again an application where we didn't know from the question data that, okay, two angles are equal, but we were able to prove that two angles will be equal. Even when they were like no, like as in parallel lines were not there clearly, right? So we figured out that, okay, these angles will be equal using like the normal angular properties. And so we were able to figure out that, okay, the triangles will be similar. Any questions up to this point? Okay. Awesome. So this is there, and similarity again we'll again re-explore when we come to questions, because that will actually throw much more light onto this thing, right? So that is there. Now a couple of things, right, should have actually mentioned in the start when discussing cosine and sine, etc. only. But yeah, just a small note, and pretty sure you would know this already, right? Like for example, for ABC, this is ABC, cos A is B square plus C square minus A square upon 2BC. For obtuse angle triangle, if the angle A is obtuse, then cos would be negative. So basically cos, like for an obtuse angle triangle, obtuse at A, this entire thing would be negative. So to say that basically A square would be more than B square plus C square. Again, these are direct outcomes of this formula itself, so no need to basically put in extra notes for this. But yeah, essentially this is the test for whether a triangle is obtuse or not. So basically you take the largest, and again in a triangle the largest angle will be opposite to the largest side, which is intuitive, right? Because The longer I keep, let's say, this base expanding, the bigger this angle will get. If I extend this to here, then it will get even bigger. So the longest in any triangle in general, the longest side will be opposite to the highest angle, or vice versa. So if you know the longest side, you can find out whether a triangle is obtuse or not by working the cosine law on this angle. If this is the longest, if for example, if let's say this was the longest, if let's say this was the longest given, then you would have to apply the cosine law on this. If basically the cosine law on this gives you a negative number, then the triangle would be obtuse. Right, because to say that, okay, if the largest angle, or if it is giving you a positive number, then the triangle would be acute. Because if the largest angle itself is giving you a positive, then the other angles are still smaller. So if the largest angle itself is sort of acute, then the other angles will automatically be acute. So you need to only test for the longest side. And this again comes on use when you have questions like, okay, two sides of a triangle are given. What can be the range of the third side for it to be an obtuse angle triangle? Right. For example, let me just take a question, right? For example, two sides of a triangle are given as anything, 10, 12, and you need to find the range of the third side such that the triangle is obtuse. Right now, as we saw that for obtuse, you need to work on the largest angle. The largest angle will be opposite the largest side. Right. Now here, if we are given this, we don't know what the largest side is. It can either be 12, it can either be x. X can be more than 12, right? We don't know what x is. But it can definitely not be 10, right? So basically, this either there would be a triangle where there's 10, 12, x, and 12 will be the largest, or there would be a triangle wherein 10, 12, x will be the largest. So you have to make a case here. So case 1 would be 12 is the largest. So if 12 is the largest, basically, then the basic properties of triangle says that the sum of two sides should be less than the third side, not even equal to, should be strictly less than. So if 12 is the largest, then basically 10 plus x should be less than 12. X should be less than 2. And also the other relation that you can get is that this angle will be the largest here. So you need to apply the cosine law here. So it would be cos of theta would be equal to x square plus 10 square, which is 100, minus 12 square, which is 144, upon 2 into 10 into x, which is 20x, less than 0. Right. So basically this would have given x square less than 44.
Hello.
Yeah.
Actually, the equation you have written, that 10 plus x is less than 12.
Yeah.
So actually, it should be greater than 12, right?
Oh yes. Oh, my bad. Yeah.
Yeah.
Yeah, it should be greater than 12, definitely. So this gives x greater than 2. And thanks for pointing that out. So and this is cos theta, which is the cosine law, and this should be less than 0 because obtuse. And again, we're only checking for the largest angle, because if it works out for the largest angle, the other angles automatically fall in place. So x square is less than 44 through this, the numerator only, because the denominator is always positive, right? 20 into a side will always give you a positive number. So the numerator is what we have to test. The numerator testing gives x square plus 100 minus 144 less than 0. So x square less than 44. So from this case, we have x less than 2, which, as you correctly pointed out, should be less than or greater than 2 actually, and x square should be less than 44. Basically, x should be less than something around 6.xx whatever. Right. So the from this case, the permissible values of x would be 3, 4, 5, and 6. Less than 6.xx and greater than 2. Usually people forget to apply the side inequality, but it is important to apply that. So if you just apply this, you would have gotten 0 to 6, but you need to have a lower limit to that as well. So 3, 4, 5, 6 from this case. If x was the largest side, this is the case 2. So then the inequality would be 10 plus 12 should be greater than x, or basically x should be less than 22. This is the first one. And the second one would be that corresponding to this angle, because it is the opposite to the largest side here, cos theta will be equal to 10 plus 12, 10 square plus 12 square, 144 plus 100, 244 minus x square. 244 minus x square should be less than 0. for an again, this is all for an obtuse triangle. So basically, x square should be greater than 244, or x should be greater than 244 root over would be 15.xxx, and x is less than 22. So x basically will be 16, 17, 18, 19, 20, and 21 from this scenario, and 3, 4, 5, 6 from this scenario. So the number of total values possible for x would be 4 plus 6 from here, so 10 values possible. Here there is no double counting as well, so it's fine. But yeah, it's good to just have that sanity check of double counting. But yeah, so x can have 10 values basically, such that, or the third side can have 10 values basically, such that the triangle is an obtuse triangle. So again, questions have come on this previously as well, so it is good to sort of see that application here. Cool. So now it may be useful to just go to the questions, right? If there are any more concepts, it may make sense to cover them as sort of as and when questions start coming up. But may be useful to go through the questions. Any doubts on the theory piece? Like any questions? And again, please be please be rest assured that we will definitely cover every what is intended to be covered in the workshop. It's not like, okay, we have said 2 days and 2 hours these, so like we are bounding it to 4 hours. If we feel that things are getting left or questions are not covered adequately, we will definitely extend the workshop as well, 2 more days or more hours, whatever suits best. So please don't be worried from that standpoint. So now coming to the questions, right? And okay, so this is the first question, and let me just go to this. So in a triangle ABC, point D, and the diagram is given. The naming is not yet done, but yeah, it says that in a triangle ABC. I'll just do the first couple of questions really, like basically to just basically show the thought process of what you can apply from the given data and from the diagram. Because again, the intent of this workshop is to basically learning how to hit the right concepts in that very limited amount of time of like 2-3 minutes, whatever. And in general, a rule of thumb is if you cannot strike the problem within the first 90 seconds, it's better to just skip it. Otherwise, you will get stuck and miss out on other quote unquote sitter questions. Right. So the intent is to basically ensure that we learn how to strike the problem as quickly as possible. So here in a triangle ABC, point D, E, and F are marked on AB, AC, and BC respectively, such that A is to EC, and like you know the ratio. So for example, point D, E, and F, so this will be D. E and F are marked, E is on AC, and F is on BC. The side ratios are given. The A is to EC is 2:3, so basically this is 2:3. BF is to CF is 3:5. BD is to AD is 5:4. Right. So just basically denoting the given data itself into the figure. Nothing happening here much. So what is the ratio of the area of triangle DEF to triangle ABC? Right. Now, first things first, if these were parallel lines, if it was given that okay, D is parallel to this, then we have already seen those cases. We can directly use similarity. Like if basically DE was parallel to BC, we could have just used that, okay, if the side ratio is 4:5, then like all the side ratios will be 4:5 and the area ratio would be 16:25. Question done, over. But the very fact that these lines are not parallel, and that is why actually you have different ratios. If this was parallel, then all the ratios would have been 4:5, or all the ratios would have been 2:3 or something, if this was parallel. And it would have been a fairly straightforward question. But now here the ratios are different, so how to tackle this? In this case, how to find the ratio of the colored triangle here to the overall triangle, right? Now, since it's the first question, I'll just write down the solution, but I'll tell you the thought process, and I'll tell you like how to do it in exam conditions very quickly. I know that the question relates to the areas. Now, what do I know regarding areas? Now, in this triangle DEF, I don't know any of its sides. So obviously, I cannot use Heron's or something here. I don't know any of the sides. In fact, I don't even know any of the angles. So in this triangle, I cannot use like half AB sine A or whatever. Like I cannot use that. In this triangle, I don't know anything. I know only for the outside triangles, right? So that should tell me that, okay, I need to calculate the outside triangles and then subtract from the overall figure to get this area, because it cannot be calculated directly. Okay, that's the step one, right? So calculate others and then subtract from the big triangle. Now how to calculate others? For example, first we take AED, and let's just quickly write what will be the area of AED. Will be half into 2 into 4 into sine A. Because again, why did I write this one? Because I know two sides. I don't know what the third side is, and this angle is A, right? Why did I use this? Because I have to compare this with the bigger triangle. So ABC is half. So if AED is, again, this is half into 2 into 4, basically, and this area is half into 2 into 4 into sine A. Using the same sort of sides, what will be the area of ABC? Will be half into 4 plus 5, which is 9, into 2 plus 3, which is 5 into sine A. And again, I'm writing this because I need to take sine A as common, so that when we take the ratio, it gets cancelled off. And again, I know that this side would be like, if this is 4, this would be 9, this is 2, this would be 5. So if this is 4 and 2, this would be 9 and 5. Again, these are ratios, these are not exact lengths, but again, we can work on ratios because anyways we're going to cancel it. So if we divide basically AED by ABC, it would be simply 8 upon 45. To say that AED is 8 by 45 times ABC. A very quick way to do it would have, like, you don't even need to write actually. You can just look at the figure. You can just basically write down this result directly, that AED would be 4 into 2 base, ABC would be 9 into 5 base. Half and sine A would be common across both of these, so they would get cancelled off. So it will be 4 into 2 upon 9 into 5, which is 8 by 45. Similarly, if we do for like this one, BDF, the area would be 5 into 3, and for the big triangle, the area would be 9 into 8. Right, so it will be 5 into 3 by 9 into 8, which is 15 by 72, or 5 by 24 of ABC. Again, why? Let me just write it down for this one as well. BDF was half into 5 into 3 into sine B, and ABC would be half. Again, we're taking everything with respect to ABC, right? And ABC here we wrote in terms of sine A, here we're writing in terms of sine B, because this is, we need to cancel the sine B. If this is 5, this entire side would be 9. If this is 3, this entire side would be 8 into sine B. If you divide this and this get cancelled, this and this get cancelled, you're remaining with 15 by 72, 5 by 24. EFC, similar thing, 3 into 5 by 5 into 8. This entire thing is 5, like this entire thing is 5, and this entire thing is, so basically by 5 into 8. So it's 15 by 40, or 3 by 8. So I've now figured out the 3 triangles, right? So I know, like, apart from DEF, what is the total area I can find out, which is basically 8 by 45 plus 5 by 24 plus 3 by 8 of ABC, right? This LCM is 360. 45 is 8, so 8 into 8 is 64, plus 360, 24 is 15, 75. 368 is 45, so 135. So this gives me 135, and 75 is 210, and 64 is 274 by 360, or 137 by 180. Is basically the area of the remaining triangle. And this is a simple, like, fraction arithmetic, so no need to worry. And so the remaining area, what would be the remaining area? Would be 1 minus of this, so will be 53 over 180. Like basically 1 minus 137 by 180, so 53 by 180 will be the area of ABC, like of DEF upon ABC. So the ratio would be 53 upon 180. Any questions?
No, it is 43, right? 43 by 180.
Okay, yeah, 43 by 180. Yeah. It's 43 by 180. Yeah. So in an exam scenario, right, you don't need to write down like even 10% of this eventually. You can just directly write down AD 4 into 2 by 9 into 5, so 8 by 45. BDF directly just write down these three numbers essentially, because half and the sine angle will always get cancelled with the bigger triangle. Just add them and get the remainder. So 43 by 180 is the ratio. Cool. So exam scenario takes like hardly like basically 30 seconds to 40 seconds. That too because like the arithmetic here took some time of the fraction. But otherwise to sort of get to the final point, it takes around like 15 to 20 seconds max. Okay, so this is one. Now going to the next one. ABC is an obtuse isosceles triangle with perimeter 180, AB 80. What is the distance between in-center circumcenter? Before even starting this problem, right? Before even like getting to the working of it, I should have in my memory that the in-center and circumcenter, the distance is given by, as we had discussed, r into r minus 2r, the square root. R is the circumradius. Small r is the in radius. Cool. So now I've written this. Now I should start with the problem. Obtuse isosceles triangle, the keywords being obtuse and isosceles with perimeter 180, AB is equal to 80. So if we draw here, AB equal to 80. What is the distance between in-center circumcenter? Now, the first thing I should directly notice right after writing this formula in my notes is that there should be two triangles possible here, right? So because isosceles it says, so the perimeter is 180. So one triangle could be like 80, 80 and 20. The other triangle could be like 80, 50, 50. Because we are given one side is 80. We are not given anything about the other side. So both these are possible. 80, 80 and 20, 80, 50, 50. Right. But that is why, like, to basically see that which sort of goes ahead, they have given the fact of that it's an obtuse triangle. So again, the test for obtuse is the same as we had discussed. The largest side, check the largest side, like either this 80 or this 80 basically. So this angle and this triangle will check this angle. So for this angle, if we write the cosine rule, so 80 square plus 20 square, like basically minus 80 square, should be less than 0, which is clearly not true. Right, so this triangle is not obtuse. 80 square plus 20 square minus 80 square is not less than 0. For here, if we test 80 square plus 50 square minus 50, 50 square plus 50 square minus 80 square should be less than 0, which is true. This is minus 6400, this is less than 0. So this triangle works. Again, cosine law, the included legs 50 square minus the square of the opposite leg. Here also included was 80 and 20, the opposite was 80. So this triangle works. So basically this is the triangle that we need to use, and that is why they gave the obtuse condition. So our triangle is 80, 50, 50, and we need to work ahead with respect to this triangle now. Okay. What do we need for this distance? We need capital R, small r. So we know the formula for both. We can calculate. Capital R is ABC by 4 into area. We know the sides. We can calculate the area. Again, area for an isosceles you can calculate by Heron's. That will also give you the right answer. But the isosceles area we covered, that would be B by 4 square by B square. This is just a faster method for this. B is the different side, A is the same side. So the different side here is 80. So 80 by 4 is 20. Root over 4 is square. 4 into 50 square, which is 4 into 2500. Basically this, and minus 80 square, which is 6400. This is the different side. So 20 root over 100, like basically this and this would give you 3600, so it will give you 60, so the area is 1200. So this is the area, and ABC we know that is 80 into 50 into 50, 2500 into like actually we need to calculate this. ABC by 4A capital R would give me 80 into 50 into 50 by 4 times of 1200. So this 4 and 80 get cancelled by 20, so this is 500 by 12. This is capital R. So let me check the calculation here. So 20 into 500 by 12. Yeah. So capital R is 500 by 12. So we know this number now. We need small r. Small r again simple. Area we know 1200. We know the semi-perimeter of this triangle, which is 80 plus 50 plus 50 by 2, which is, and actually the perimeter is already given. So semi-perimeter would be 90 directly. So the small r will be 1200 upon 90, area by semi-perimeter. So which is 120 by 9 or 60 by 3. So 120 by 9 or 40 by 3 actually. Right. This actually also can be reduced to 125 by 3. So capital R is 125 by 3, small r is 40 by 3. Okay, let me just create some space, or maybe we can write here. So we know both the numbers now. The distance between the in center and the circumcenter would be 125 by 3 into r minus 2 times r. So 125 by 3 minus 80 by 3. So which will be 45 by 3. So 1 by 3 comes out. This is 5 cube into 45 is nothing but 3 square into 5. So 1 by 3 into 5 square comes out and 3 comes out. So this will be 25. This will be 25 is the answer. Any questions? Again, wrote the formula and then just check that how can I get to those parameters. So if I can get r and a small r from this, the question is done basically. Then after that it's just calculation. Any doubts on this? Okay. Yeah. So this is a concept that we haven't discussed till now, and was more useful to discuss this with this question. So before we start with this question, right, there is a set of very standard formula that is there for this, for the number of triangles with integral sides for a given perimeter. So if perimeter is even, if P is even, the number of distinct triangles with integral sides, obviously if you allow fractional sides, then there are infinite triangles. For integral sides, if P is even, then the number of triangles is P square by 48. This everybody knows. The key point to this is this function is the CIF, or the closest integer function, not the greatest integer, not the least integer, the closest integer function. So like 8.4 will be 8, 9.6 will be 10. So whatever is the closest integer, that would be the number of triangles if P is equal to even, if P is equal to odd, and this is the total number of triangles, right? If P is equal to odd, it will be this P plus 3 whole square over 48. This is again the closest integer. All these formulas are closest integer function. P plus 3 whole square over 48. This is total number of triangles. Right. If you want to find, okay, out of these total, how many will be scalene triangles? Like with all different sides. So, yeah.
Can you explain it once more?
Sure. So if the given perimeter is even, so for example, if the question is that, okay, how many distinct triangles with integral sides are possible with a perimeter of 20? Now 20 is an even number. You just write 20 square by 48, calculate whatever it gives you, and take the closest integer to that. Like the general rounding principle, right? Basically, like if it's like less than 9.5, it will be 9. If it's more than 9.5, it will be 10. That's sort of the general rounding that we do, right? It's not the greatest integer, it's not the least integer. It's just the closest integer. And we'll see it in this question as well. So this is for the total number of triangles, the formula. If we are doing for scalene triangles, like all sides are different, how many triangles, like it will be a subset of this. So just replace p by p minus 6 in the above formula. Just replace p by p minus 6. So if the perimeter is even, the number of scalene triangles, if I replace p by p minus 6 here, will be p minus 6 whole square by 48. Again, the closest integer function. If p is equal to odd, I replace p by p minus 6 here to get p minus 3 whole square by 48. Okay, so I have the total triangles now. I have the scalene triangles now. So if I subtract them, what will I get? I will get isosceles triangles. And equilateral is also considered like within the isosceles only. Right, so isosceles, if I want to find out, it will be total minus scalene. Obviously, right, like all sides different, like all total number of triangles minus the all sides different case will be the isosceles triangles, and this isosceles triangle will include the equilateral case as well. So in general, if the question only asks isosceles triangle, right, you need to include equilateral there as well. If the question specifically mentions that isosceles but not equilateral, then you will subtract 1 if there is an equilateral triangle possible. For example, in this case, the perimeter is 47 units. There is no equilateral triangle possible. If it was, let's say, 51 units, like a multiple of 3, then one equilateral triangle would have been possible. But that still gets counted within the isosceles. When you do this funda, you just still get counted there. So if they only ask you for isosceles, you have to include the equilateral. If they specifically ask isosceles but not equilateral, you will just subtract 1 here. In this case here, it is not relevant because 47 anyways won't have any equilateral triangles. Right, so now with these bunch of formulae, right? So if we try to do this question now, it's a fairly straightforward one. Perimeter 47, isosceles would simply be total minus scalene, as we just saw. Total for an odd perimeter is p plus 3 whole square upon 48, so which is 50 square by 48, the closest integer function. And the scalene would be p minus 3 whole square by 48, which is like p into p minus 6 if you replace that formula, so it will be 44 square by 48. Again, the closest integer function. Now, to the query that somebody had, right? Now, if we actually use the calculator to calculate 25, like 50 square by 48, it gives me a number of, I just did it live, so it gave me a number of 52.08. Minus, if I do the same here, so 44 into 44 by 48 gives me 40.33. The closest integer of 52.08 is 52, minus closest integer of 40.33 is 40. So there will be 12 isosceles triangles. Right, so this is from the formula, and this, like, again, it so sort of is, if they ask you this question, they are expecting you to use this formula. Right, the other way to do this would have been if somebody doesn't know the formula, for example, right? So the perimeter is 47, you have sides AAB for an isosceles triangle. So 2A plus B would be equal to 47, and also we know that sum of two sides is greater than the third side always. So 2A should be greater than B. So basically, if you see that for 2A should to be greater than B, then basically 2A can only go up to 24 basically. Sorry, B can only go up to 23 basically. And this is again only for, like, if somebody doesn't know the formula or isn't able to recall, 2A would be greater than B. So from this equation, the sum of these two is 47 and this has to be greater than this. So B can only go up to 23, right? Because after 24, B will start getting greater. So B can, the maximum value of B can be 23. So basically the 2A, the limiting value would be 24. If B is 23, the 2A would be 24. So A would be from 1 to 12. These are the 12 triangles. In case you don't want to remember the formula, but this formula is useful. But this is another way to calculate the isosceles triangles, that maximum B can be 23, so 2A can go up to 24, so A can go up to 12. Right, so this is the part A of the problem. Now, in terms of parts B and C, right? Okay. All sides odd, you can again take the side that's 2a minus 1, 2b minus 1, and 2c minus 1. These are odd numbers, right? So all sides odd would be 2a minus 1, 2b minus 1, 2c minus 1. Now, a good question would be like, why not 2a plus 1, 2b plus 1, 2c plus 1? Even those would be odd, right? But we are not taking that. Why? Because we want A, B, and C to start from values of 1, 2, 3 onwards. If I take 2a plus 1, I will be starting A from 0 essentially. I want to start A, B, and C from 1, 2, 3, etc. Not from 0. So that's why 2a minus 1 works, because here you will be starting from 1. So if all sides are odd, you have sides at 2a minus 1, 2b minus 1, 2c minus 1, and always take, like in case of all odds, all even is pretty straightforward, like 2a, 2b, 2c, but all odd would be 2a minus 1, 2b minus 1, and 2c minus 1. Again, because we are willing to not start from 0. So the perimeter is 47 as given. A plus B plus C would be 25. This we already know. This is in a shape that we already know. So this, the number of triangles with this would be 25 plus 3 square by 48. This is because 25 is odd. So this formula again, like the one we used for 47 in the beginning. So 28 square by 48, the closest integer of this. If I check this via calculator live, this is 16.33. So the closest integer would be 16 triangles. Would have all sides as odd. Okay, so all sides odd would be 16. C is just directly a sort of a result of the above two. Essentially, like I know the total triangles. So basically, if a triangle has an odd perimeter, right? What cases can there be? Either all sides will be odd, or it will have two even and one odd. There's no other case. Two odd and one even will give an even perimeter. So here we have an odd perimeter, so there can only be two cases. Either all sides will be odd or two even, one odd. All sides odd, we just found out that 16, right? Total we know was 52 here. We have found for this part 52 plus 2 even 1 odd. So 2 even 1 odd will be 36. 52 minus 16 is 36. So again, just to recap, total odd perimeter 50 square by 48, 52 triangles. For isosceles, subtract scalene, got 12. For all sides odd, found it by the 2a minus 1, 2a minus 1, 2c minus 1. And for the 2 even 1 odd, just basically subtracted the all sides odd from the total, because there's no other case possible. Cool. So this is another concept. Going to the next question here. A square is, and again, any questions till now, like any concerns till this point? Okay.
Sir?
Yeah.
Yeah, for the last question, that is two
Yeah.
even and one odd. Can't we do like this, like 2a plus 2b plus 2c minus 1 equal to 47?
No, actually that we cannot do, because that this formula, right, this triangle's formula of p square by 48, right, is valid only when like all the three sides have same conditions on them. For example, either like there is no condition, like a plus b plus c equal to 47, we were finding total number of triangles, no condition on any of them. So it will be 50 square by this.
Okay.
Or for all sides odds, it is the same condition on all the three sides. So the formula is right, keeping that symmetry in mind with respect to the variables.
Okay.
So that's why you will always need to, so even if the part B wasn't there in the question, right, even if it directly has to 2 even 1 odd, so you would have to calculate the all sides odds
Okay.
to reach this. So, but yeah, good question. That why can't we take it that way? Square is inscribed in a triangle ABC as shown, side parallel to the base. So okay, let's first name this triangle is. Yeah. AB is 20, AC is 34, BC is 42. Find the side of the square. So this is a square, so we need to find the side, let's say x. We need to find this. Now, first things first, like this question looks deceptively simple, right? Like basically it looks like, okay, a lot of data is there. This should be easy to find out. Now, if you've not seen such a question before, the general tendency would be like, especially in exam scenarios, right, would be people would be starting to figure out like, okay, if I can find this angle, I can get this side, right? Or something to that effect, basically, right? That, okay, parallel, okay, maybe similarity can be applied, but how? Right, because I sort of don't know the sub-segments of this triangle, right? Like, okay, how much of 20 is within this, within this, within this, within this, or how much of 34 is split, how it is split. But I definitely cannot find the angles, etc. there. So for a person who's not seen this question, they will most likely go the route of sort of trying to apply some sine rule here or some trigonometry based on, okay, this is 90, maybe I can apply something, but it won't. Either it will be a very lengthy process and they won't get to the answer. So again, the major hint here is the square means that the side is parallel. So similarity can definitely make our life easy to an extent. Right. So I can immediately say that, okay, if this square is PQ, R and S, I can immediately see that PQ parallel to BC. Basically, so PQ by BC will be same as AP by AB will be same as AQ by AC. Why? Because triangle APQ similar to triangle ABC. Once again, why? Because of parallel lines and these angles are equal, corresponding angles. So these are similar. So as we had discussed, that the side ratios will be the same. Now think about what will this give me. Now PQ by BC, okay, x by 42. So at least I have one equation where there is an x. But AB I know is 20, but AP I don't know. AQ I don't know, AC I know is 34. So it won't give me anything, right? Like AP by 20 equal to AQ by 34. It could have been useful if either AP or AQ was given, so we could have used that part of equation. So suppose if AQ was given, we could have used these two. Or if AP was given, we could have used these two. But they are not given, and there's no direct way to find them out. So basically, these ratios may not be able to help us, even though they are correct. Right? So we cannot find x or any leads into x by these equations, right? So okay, what is the alternative? I definitely know that the lines are parallel, so similarity should be giving me something. Now think about what else similarity gives me that we had discussed also. We know that if APQ is similar to ABC, similarly like BVR is similar to the big triangle QSC. We had discussed it before, right? Similar to the big triangle because of parallel lines and like again corresponding angles equal and stuff. So all these small triangles are similar to the big triangle, fine. But we don't have any of these smaller sides, cannot use them. What we can do is that since APQ is similar to ABC, the ratio of sides will be similar to the ratio of heights, as we had discussed. I can find out this height, right? I can find out this height. This height, the entire height I can find out. I know that this portion is x, this is a square. This height I know, this height I know, I can figure out this. So for example, what will be the height of AM? Height as in the perpendicular. So if I were to draw perpendicular here as shown, so for AM basically, right? How can we find out AM? For area of area of a triangle, we know that half into base into height, so half into 42 into h. Also, we know that all the three sides are given, so we can use the Heron's formula as discussed to get the area. So the semi-perimeter here, if we quickly calculate, 20, 34 is 54, 54, 42 is 96. So semi-perimeter is 96 by 2, which is 48. So this will be root over 48 into 28 with respect to 20, 6 with respect to 42, and 14 with respect to AC. So this is again if we 48 is 2 power 4 into 3, 28 is 2 power 2 into 7, 6 is 2 into 3, 14 is 2 into 7. 2 total power is 4, 2, 6, 7 and 8. So outside comes 2 into 4, 2 power 4. Sorry, so 3 total power is 3 square, so outside comes 3. 7, the total power is 2, so outside comes 7. So the area is 16 into 3, 48 into 7 is 336. So H will be basically 336 by 21 from this equation, which is equal to 16. So I know that this entire height is 16. And again, how sort of was I inspired to find out the height? Because I knew that the ratio of side would be same as ratio of heights for similar triangles. And again, as we had discussed, that this would be the same as ratio of in radiuses, circumradiuses, and etc. everything. So here we are using the altitude proportionality, right? So now the height is 16. So if this entire thing is 16, this is 16 minus x. So I can say that x by 42, the ratio of the sides, will be the same as ratio of heights. So PQ by BC, which is the x by 42, will be the same as 16 minus x by the whole thing, which is 16. Of the big triangle has the whole height, right? 16. So this is 16x. 42 into 16 will be 672 minus 42x. So x will be equal to 672 by 58. This is the side of the square. You can reduce it further, obviously, but yeah, 672 by 58 is the value of s or a side of the square. So again, very good question in terms of applying the fact that similarity works on the ratio of heights as well. Because people generally forget that it works on those. But once you've seen it now it like you any figure of this sort, then you'll be able to sort of handle, because immediately your mind will go to the fact of this. Any doubts? Okay, this is a CAT 2017 question, and again you'll see that CAT will never test like complex concepts or like basically lengthy applications. So if you feel that the method that you're thinking in a certain geometry question is going to be too lengthy, like 3 or 4 angles, sine or cos to be figured out, etc., etc., there should definitely be a shorter way that you would be missing out. CAT will never test like complex things or like lengthy stuff basically. CAT will test the basic fundamentals and the like whatever we have discussed, right? So some application of that. So as you can see, right, this is a CAT 2017 question, and we'll try to do this, and we'll see that like basically how much complex this is. And this is not like that much old, this is 2017 only. So it's a right isosceles triangle, which is ABAC. Okay, I can mark arbitrary actually. Right isosceles triangle, so this is equal to this. Distance from ABAC. Okay, a point P is marked. AB, BC, and AC, it's equidistant from the 3 sides. Distance from this is equal. So by definition, what is P then? P is, even if it's not writing in the question, P is the in center, because it's equidistant from the side will be discussed. This is equal to, so PM, PN, PQ is equal as given, and this distance is given as 4 into root 2 minus 1. So this is the in radius. So the first thing from this question that you need to, even before like putting pen to paper, you need to figure out is that the distance from the 3 sides is equal. Okay, the point is in center, and the distance that is given is the in radius. That is the first conclusion that you need to draw even before starting out the question. Now, okay, I have the in radius. Correct. Hello, does somebody have a question? Okay.
So yes, I was saying that
Yeah.
We can get a height directly from P, as you mentioned that a point lying inside a triangle and is equidistant from all the sides. It
Yeah.
resembles the height of the triangle.
No, that okay, you're confusing. That is only for equilateral triangles. For equilateral triangle, the sum of these three would be the height.
Okay.
Okay, like just as a side note, and again, please do not get confused. Only for an equilateral triangle, if there is any point P, then this distance plus this distance plus this distance would be equal to the height. Here it's a right angle isosceles triangle. Right, so I know that the in radius, so the first thing, okay, was sort of striking the fact that this would be the in center and this would be the in radius. Now I know that the in radius in a right triangle is basically P plus B minus H by 2, right? The sum of the legs minus H by 2, as we had seen over there as well, right? Here, since it's an isosceles triangle, so the P and the B are equal, basically, right? This is equal to this, right? So if I denote like, okay, this is in our typical notation of opposite to C is C, opposite to A is A, and opposite to B is B. So this is basically then A, this is basically A plus C minus B by 2, which is 4 square root 2 minus 1. But here A is equal to C. And since it's a right angle isosceles triangle, what else can we figure out? Isosceles triangles mean this will be 45 degrees. So it will be a 1:1:2 root 2 kind of a setup. So if this is C, then this would be C root 2. So this is 45 degrees. Right. So 1:1:2 root 2 sort of a setup. So A will be equal to, so it will be like C plus C minus C root 2 by 2. Again, let me just repeat. Isosceles triangle, so A and C would, the legs would be equal, and since this is isosceles, so this will be 45 degrees, so it will be like 1:1:2 root 2. Root 2 using the sign of 45, or basically using Pythagoras. So this is the 4 square root 2 minus 1. So if I carry 2 here, so it will be 8 square root 2 minus 1. And so this is 8 square root 2 minus 1 equal to, take C common. So this will be 2 minus root 2. So C would be 8 root 2 minus 1 upon 2 minus root 2. This looks a bit untidy, so we can obviously simplify this a bit further. Root 2 minus 1, if you take root 2 common here, you will get root 2 minus 1 inside as well. These two get cancelled out. 8 by root 2 is nothing but 4 root 2. So I know that this side is 4 root 2. Now this side is 4 root 2. This is an isosceles triangle. This will also be 4 root 2. So the area is half into 4 root 2 square. Half into 32, which is 16 units. Square units actually. This is the area. Done. Again, just the only thing to figure out was that this is the in radius, and just to basically link it to the expression for in radius that we know for a right triangle. This is for a right triangle only.
Sir.
Yeah.
Can you explain how P is in radius of this isosceles triangle?
So isosceles is given, right? And the in radius, even if it was not an isosceles triangle, by the definition, when it says that its distances from AB, AC, and BC is equal, so any point which has an equal distance from the three sides will be an incenter. And obviously this distance then will be the in radius. So the distance equal being should tell you that it's an incenter, and that distance itself would be an in radius. So this would be small r, small r, small r, and each would be equal to 4 into square root 2. This is the definition of an incenter as we discussed. And then it's just linking that, okay, this in radius is, we know this distance is the in radius, fine. And then the P plus B minus H by 2 that we have studied for a right triangle. So sum of the legs minus the hypotenuse by 2. And again, using that this is isosceles, so the legs would be equal as like you would expect an isosceles triangle. Make sense? Okay, hopefully it is clear. Again, a CAT 2019 question, even more recent than the last one. ABC right triangle, altitude AP on hypotenuse BC. Okay, this figure is already drawn. So it's a right triangle and ABC. Altitude AP on hypotenuse BC. Again, this setup that we discussed, right? That if it's a right triangle and there's an altitude, like a right triangle and you shooting a 90 degree from a 90 degree, shooting the 90 degree altitude from the vertex of the 90 degree. This is AP. So we had seen this result that AP square was actually no, BP square was actually the figure is not named correctly as per the question. ABC is right triangle with altitude AP. So actually this should be A. This should be B and this should be C. Yeah. So we had seen that for a right triangle where again the 90 degree shoots the altitude to the side in the front. So AP square was equal to BP into PC. This we have seen. Correct. Now, if BC equal to 20, so this entire thing is equal to 20 actually. And we know this. Now, anytime that we have to find the maximum or the minimum of something, there are a couple of things that should definitely come to mind. The first and the foremost of those things should be AMGM, arithmetic mean, geometric mean, saying that AM should be greater than or equal to GM. So if we apply the AMGM here, basically, right? So basically BP plus PC by 2 should be greater than equal to the geometric mean, which is BP into PC. BP plus PC I know is 20, so this will be 10. BP into PC is AP square, so the root will be AP. So AP should be less than equal to 10, so AP max is 10. That's it. Over. So just a simple result that when you're drawing a perpendicular from the 90 degree, and this holds true in any right, like in any basically case of perpendicular from a 90 degree. So this and this PR square will be equal to QR into RS, product of the segments. So here the segments are, as you can see, BP into PC and AP square. So it's an AMGM thing because, and how did I strike on the AMGM thing? Because I saw the word maximum. So this sort of gave me that inequality. So it took me like, what if you like in an exam scenario, this would like again take 30 seconds to do this if you know this result. If you don't know and you have to derive, then yes, then it sort of starts taking time then. Okay.
So in short, we can conclude that maximum length of AP is equal to hypotenuse by 2, right?
In this case, yes. Like when you're dropping the perpendicular, yes. Yeah.
Okay.
So triangle ABC, circle BC with diameter BC is drawn. And again, the purpose of this question is to show you that what level of sort of conceptual clarity or fundamental base CAT is expecting you to have. All of you must be knowing the concepts obviously, but like in general, this is the way to sort of apply it in an exam type of a scenario or in a mock setup. In a triangle ABC, a circle with BC diameter BC is drawn, intersecting ABAC is the length of this and this. What is the length of BQ? CAT 2080. First things first, circle with diameter in a triangle. There's a first triangle ABC. First of all, let's just keep drawing it as we read the question. Circle with BC diameter is drawn. Okay, let's draw a circle with diameter BC intersecting AB and AC at points P and Q. So that it will intersect AB somewhere and BC somewhere. So this will be the circle of there. Something of that. And this is BC the diameter. This is important. Right. So if the length of AB, AC, CP, so AB is given as 30. Okay. AC is given as 25. CP is given as 20. And okay, P and Q, let's just label them. CP is given as 20. What is the length of BQ? So just to be asking in BQ. This one. So first of all, let's understand that what all things we can apply, like even before sort of again putting pen to paper, we know that there's a diameter BC, right? Now, what does the diameter? Two things it should immediately tell us that okay, like obviously half of this would be radius, so you can figure out, like let's say if you join this point to P, then this would be the radius, and etc. etc. We can do that. The second thing they should tell you that the angle subtended by the diameter on the circumference is 90 degrees. So you should immediately start marking like whatever angles are available are 90 here. So for this will be 90 because this is subtended by the diameter. This will be 90. Both of these are 90 degrees. I know this, I know this, I know this. Whenever, and this is a sort of a mini principle in any scenario where you face this. If there are like more than one perpendiculars, right? A good idea is always to equate the areas. Right. Basically because perpendiculars directly give the area, right? Half base height, half base height. So if I have like this height and this height, so their bases can be found out, right? So, and this would be useful in any circumstance where you have like more than one, or like these are altitudes, right? Perpendiculars. So equating areas should usually work. So if I talk about the triangle ABC, like the whole triangle ABC, the area would be half into AB into PC, because this is the height. Why is this the height? Because this is 90 degrees. Why is this 90 degrees? Because this is the diameter. Will be equal to half into AC into BQ. AB I know is 30 into PC. PC is 20 equal to AC. AC is what? 25 into BQ I need to find out. So BQ is simple, 1320 is 600 over 25 is 24 units. Over. Again, not a complex question really. But yeah, the thing, so the two tricky parts in this question was like first, basically that is why if you see it in the previous questions, there was a diagram. But here there isn't a diagram. So first converting this into a diagram is the first part. And second, just realizing that angle in a semicircle is 90 degrees. And that's it. Very, very, very short and direct question otherwise. So it shouldn't take time. So that is there. Now this question, again, any questions, or if you guys would like a 5 to 10 minute break, do let me know. Like just interject me at any point that okay, like fatigue is starting to set in or something, and we can stop at that point. And again, the coverage, like all the questions that are in this list, and these questions have been like carefully handpicked as well. So all these questions would be covered. It's not necessary that the work, like if we need to do the workshop beyond tomorrow as well, we will do it and we will cover everything. So don't be worried on that. Now this is okay. KVNs are lines basically like random lines inside a triangle. For example, this line. Now this may not be a median, may not be an altitude, may not be a perpendicular bisector, angle bisector, anything. Just a random line drawn from a vertex to a side is called a KVN. So all these medians, perpendicular bisectors, altitudes, angle bisectors, all these things are special cases of KVNs. Right. Okay. KVN AD is drawn to BC in a triangle ABC with AB 18. BC, okay, sides are given. Again, it seems like a lot of things are given, so should not be that tough, but let's see how to deal with this. AB 18, BC 36, AC 30, BD, okay, KVN AD is drawn, so BD is 11. BD is 11, so I can automatically figure out this will be 25. Now I need to find out AD length. Now again, this is a very deceptively simple question because again, it seems that, okay, I know, like even for the smaller triangles, I know some of the sides. So like 11 is given, so I found out 25, fine. I need to find out AD. So maybe I can apply some cosine rule here, then equate it to something else and get that. Now there is a process for that. Now that will be lengthy. Because see, if you just start like, so sort of again, if you just see these values and start off doing the questions, right, you will get stuck, and that is why they have given that question. They want you to get stuck in a like loop of like applying equations after equations, that will give you the answer for sure, but it will take you time, right? So whenever such question comes, right, wherein like these sides are given and a certain side inside is asked, just write those values down once. 18, 30, 18, 30, like from the diagram directly, right? 11, 25, 36. These are the numbers, right? So again, the long method should be avoided. The point being, now cosine and sine rule are very, very useful, but in this case, if you see that they may not, like they will not be able to give you something directly. Why? Because we don't know all the sides of any triangle here, or we don't know any angle. So you'll have to find the cos of every angle and then basically equate it to get the answer, which takes time. If I just see the sides like 18, 30, 11, 25, 36, these are just the numbers from here. Now, if you observe something, right, that 18, 30, 25, 36. Right. If you observe something that this basically this 30 and this 25, there is a ratio of 5:6. Correct. Similarly, between 30 and 36, there's a ratio of 5:6. I'll explain this question from the starting as well. But just follow along that basically what I'm doing is I'm writing the sides and I'm sort of looking, just observing the ratios into which these sides are built. 25:36 gives me 5:6. It is like like visible. Sorry, not 25:30 gives me 5:6, and 30:36 gives me 5:6 as well. So in a way, I can say that DC, like, or CD by AC is equal to AC by BC. This by this is equal to this by this, equal to 5/6. This is again just from observation that the sides are, once I figured out that this was 25, which is 36 minus 11, I observed that this is 5:6 and this is 5:6. So maybe I can construct two triangles wherein sides are proportional. Right. So if I talk about this triangle, the small, like, because like the sides are part of this triangle, so ADC, I know that, okay, the numbers that I'm involving are 25, 36, and 30. So which means this triangle is getting involved and this big triangle is getting involved. This triangle is getting involved because 25 and 30, and this big triangle is getting involved because of 36 and 30. So ADC can be similar to, now first triangle I can write any way I want. The second triangle, the naming is very, very key. So CD has to be matching with AC. So the last two alphabets should be AC. And AC has to be matching with BC. So the first and the third alphabets have to be BC. So the third alphabet will be C, this will be A, and this will be B. Again, let me just repeat. ADC I just wrote. Now I know that CD by AC is AC by BC. So AC, so basically CD is the last two alphabets here, so these should match AC. In what order, we don't know yet. To figure out the order, we need to look at the other equation. So AC by BC. So the first and the third should be the first and the third here. So C should both be in the second and third place, and the first and the third place. So which means C should be in the third place. And you can always check, right? So if this equation, so CD by AC gives you first and a third, AC by BC. Naming a triangle is extremely critical in similar triangles. And obviously, like, both these triangles have a common angle C, which is the included angle. So basically, this and this side we're using for proportionality, and this is the included angle. Right. So that is why angle C is common. So basically, you can say that by SAS similarity, these triangles are similar. Any doubt? Again, why is this the included angle? Because these and these sides were getting involved in the similarity proportionality. and this is the included angle, which is common for this small triangle and the big overall triangle. Now, once this you have figured out, then it is extremely simple. AD by AB will be equal to, let's say, AC by BC. AD by AB is AC by BC. So AD by AB is what? 36. AC is what? 30 by BC is what? No, AD by AB is 18 actually. Is what? 36. So AD will be 2 times and 15. Tricky question, but a very good question to sort of exhibit that if like you should not like just jump onto the sort of writing down like equations after equations. Sine cosine rules are very useful, like very applicable, but when you have like sides and angles given in a certain way, or like the equations are clearer, like basically if you had something like this angle was given or any angles were given, then it makes sense to sort of use that, because otherwise you'll have to make variables and it gets very muddy thereon. So this is just basically that observing the sides and observing that in combination, basically these sides are proportional. 25 and 30 at the same proportion as 30 and 36. So very good question to exhibit that similarity is not directly given, but you can establish similarity using proportionality. So here we derive the similarity. Any questions? This is one of the more tricky questions that we have for the set, but it's so useful to demonstrate that how, like once you are able to establish similarity, how simple the question gets. Okay. Trivians or trivians maybe. BD and C in a triangle ABC intersect at point F such that area DFC is 5, area BFC is 10, area EFB is 8, and find the area of quadrilateral AFD. And please guys, if you feel that I'm going fast or something, please let me know. We'll adjust accordingly. Now, first of all, this question, even like before making the diagram, this question is all about areas, right? There's nothing given in terms of sides, angles, like anything basically. Just areas are given. So, okay. Intersect at a point F, area DSC is 5, area BSC is 10, EFB is 8, AEFT. So this quadrilateral area has to be figured out, right? So what, okay, so basically before we start the problem, right, in terms of area, what are the things that we know? We know to calculate areas by like 6 or 7 different ways, right? But in all of those ways, something was given in terms of length. Either side length was given, one angle was given, maybe the radius was given, circumradius was given, something was given basically, right? And we use that to calculate the area. Here nothing is given. Here just areas directly are given, right? And you need to, and again, it's not at one glance you can figure out that it's not feasible to make equations for every triangle. Okay, like half base height is, you will have like 20 variables and you will get stuck. It's not actually get stuck, it is not even possible to solve this that way, because there'll be like too many variables. For every triangle there'll be a separate base and a separate height. So it should be clearly visible that that is not the way to go. So what can be done? Like find the area of the quadrilateral. Now directly, obviously, area of quadrilateral is difficult to find. Let's just draw a line here. Call this X and call this Y. Now, what property of area do we know? We had studied something called the base area ratio, right? That the ratio of the base will be the ratio of the areas of the triangles. Again, just to sort of put it in perspective in terms of a small revision. So if this was, let's say, m is to n, the area of this triangle will be m is to n, right? So can we use that here? Because we don't know anything apart from areas, right? So we can only use like area-based ratios. So that should be the first thing. And secondly, again, like figuring out sides and all, as we just mentioned, is crazy. So now if we see this triangle, right, x and y. Now observe this line AB carefully. This line AB. So along AB, right, if we now AE by EB will be equal to x by 8 by the base area ratio. X by 8 is AE by EB. Also AE by EB, if you see the bigger triangle, like the whole triangle, then AE by EB is this entire area by this entire area. So basically x plus y by 5 over 18. So whatever lying in this part and whatever lying in this part, the ratio of that. For the smaller triangle, this was x by 8. Like for AFB triangle, it was x by 8. So I know that x by 8, because they lie on the same base, so x by 8 is equal to x plus y plus 5 by 18. So basically give us one relation at least, which is 10x will be equal to 8y plus 40. Yeah. So this is one. Now can I get another equation like this? If I am able to get another equation, then this is done then, right? Now let's see. Now I know 8, 10 and 5. So I can see that if I make an equation, let's say along this line across BD. So here I'll have 10 by 5, which is 2. So I'll have like one thing as a given. So along BD, if I see, so in this triangle in BDC, BF by FD equal to 10 by 5 equal to 2. Also BF by FD in this triangle, in the triangle on the other side, is equal to 8 plus x by y. 8 plus x as like corresponding to this part and y corresponding to this part. So basically 8 plus x equal to 2y, x equal to 2y minus 8. You put this here. So 10 into 2y minus 8 will be 20y minus 80 is equal to 8y plus 40. Y equal to 10. 120 by 12, that is. X will be equal to 2y minus 8, which is 12. So x plus y will be equal to 12 plus 10, 22 is the answer. Yes. Again, a very good question, like exhibiting the base area ratio concept here. And this actually, now that you've seen this question, now you'll not forget this like ever, basically. Like wherever these segment areas are given sort of, and you're asked an area of a different segment in a triangular setup, base area ratio will always come to the rescue, right? And there is like again, like there are concepts around mass point geometry, etc. that will also help us to figure this out. But again, no need to get into this. Just remember that the ratio of area will be the same as ratio of base, like in sort of adjoining triangles. So now whenever you see this figure, you will be immediately reminded of this. Okay. This actually, a variant of this question came in CAT 2019, if I'm not wrong, or 18 probably. Any doubts on this question?
Yeah, sir. How much long can you do this class?
Yeah, maybe this will be the last question now, like the next one.
Okay.
Okay, and then we can probably call it a day, and then we can continue tomorrow. Right.
Okay.
They're around actually like around 22-ish questions probably total in terms of like actually around 20 of them are from triangles, and the next 2 to 3 were from polygons, but since we can't cover them today, we'll definitely continue from this point on tomorrow. And tomorrow actually we can start early if you feel like that's helpful, let's say from, let's say, I don't know, maybe 7 p.m. or something, and then go until 10:30, 11.
Yeah, that would be fine.
Yeah, okay. So we can start early, no problems there. A variant of this question came in CAT directly, and it's again a very direct result there. But let's derive it so that again mugging up shouldn't be the approach, really, right? So medians AD and B of a triangle ABC are 15 centimeters and 8 centimeters respectively, intersect at 30 degrees. Find area of the triangle. This template question you will find in many places, even in mocks. Like two medians will be given, the lengths will be given, they're intersecting. Either they're perpendicular, in which case this 30 will be 90, and etc. etc. So it's just good to have a certain standard approach in mind, right? Now, this is a triangle. And let's just forget this question. Let's just basically get the result itself and derive it. This is theta basically. Again, for this question is 30 degrees, but we are trying to derive this more generally. Medians means midpoints. Okay, this does not look like a midpoint, but assume for now it's a midpoint. And so this is the midpoint of this side, this is the midpoint of this side. Okay, that much we know. This is where the medians are intersecting, so this will be the centroid, that much we know. And we know that the centroid divides the median into a 2:1 ratio, right? So if we look at this triangle, let's for conversation's sake make the third median as well. It will pass through the centroid and it will be something around this. Like this is, let's just complete the figure with a third median as well. So this will be it. So we know two things, right? So first of all, the centroid divides any median into 2:1. 2 being the like the side, like the origin of the median, basically the vertex side. And second, we know that if all the three medians are drawn, then every triangle is 1/6 the entire area. So if I can find the area of one triangle, I can multiply it with 6 into area of one triangle to get the total area. Okay. So now if we just see this small triangle AGN, area would be equal to half into AG into GN sine theta, using the area of triangle concept. AG, now it is 2:1, right? So half into AG will be 2/3 of AM. AM is the median, which is given like the midpoint to the median. GN is this much. This is 1/3 of the median. Why 1/3? Because 2:1, but 2 is this part. 2 is the part facing the vertex. So 1/3 into GN into BN. So BN is the total median sine theta. So this basically gives me 1/9 into product of medians. AM is the median, BN is the median. So I've written this expression in terms of medians. So product of medians into sine theta. This is the area of one small triangle. As we have discussed multiple times, that 6 into this will give you the total area. So 6 into this will be 6 into 6, 1/9, so which is 2/3 into product of medians into sine theta. This is the standard result that you can directly apply. So here the medians were 15 and 8, theta is 30. Area of the entire triangle will be half, totally 2/3 into product of medians 15 into 8 is 120 into sine 30, which is half, 40 over. The CAT question was like it gave that the medians are like probably for 9 and 12 if I'm not wrong, and the intersected they mentioned that the medians are perpendicular. So perpendicular medians means this will be 90 degrees, and they had asked the area directly. So people who would have like seen this problem or like known this result, because it's a fairly standard one, would have directly applied 2 by 3 into 9 into 2 sine 90 is 1. So 2 by 3 into 9 into 12 is basically 72 would be the answer in that case for the CAS problem. Again, it seems the length for 9 and 12, but yeah, like basically, yeah, this is the concept. So once you know this, nothing doing, you can just directly apply this. Again, the purpose is not to like cram these things up, but once you sort of do a question on this, right, then it becomes much easier to sort of recall at that point that, okay, I've seen something like this earlier. And that is why sort of I put these questions in this list so that it becomes easier to strike those concepts in the exam scenario. So that you can easily figure out that, okay, this is similar to something that's already studied. So again, obviously it's getting a bit late now. So let's stop here for the day, but just to sort of, I'll just like flash through the slides quickly. So in case any questions that you would have, let's say, have right now, and I'm happy to take them up. This was general area ratios, which could be just solved really quickly.
Yeah, sir.
Yeah, please go ahead.
In the last question, the product of median refers to the product of any two medians, right?
Yes, yes, any two medians, and the angle also has to be between those two medians only.
Okay. The angle will be the larger one or the lower one?
Okay, first of all, it won't matter, right? Because sine theta is sine 180 minus theta.
Oh, okay. Okay. Yes.
Yeah. So this was again the sort of the oral question in terms of, okay, you can just write these areas directly by 4 into 2 upon 9 into 5, etc., etc., so on and so forth. This was the in-center circumcenter. You know the distance. You figure out R and R. Again, the only tricky part was figuring out that the triangle to go ahead with this and not the other one because of the obtuse condition. This is a fairly standard direct, like it's an algebra question more than a geometry question, but yeah, it is helpful to know this. This is again a good application of the fact that similarity is the ratio of heights. We didn't know any side or anything for that square, and we were still able to figure out because the ratio of side was same as ratio of heights. This is again completely, this is a CAT question dependent on the fact that the distance, if it is equal from a single point to the sides, then that point is the in-center, radius is the in-radius, and it was given, then it's a right triangle, so the perpendicular plus base minus hypotenuse by 2 result directly just sort of ended the problem then and there. Maximum length is AMGM. This result of from a 90-degree vertex to the perpendicular, if you draw, this result is fairly important. And then this was very simple, like just equating areas basically. This was a tricky question because it is hard to strike the similarity proportionality, but once you do this, again it ends there. But yeah, the only thing was just the like observing the sides and observing that similarity exists. This is base area ratio. Great question to sort of exhibit that concept. This is a standard result which we just derived, and now that you know the derivation also, so it you'll not forget how to apply this now. It should be okay. So yeah. So again, at least the concepts till now, like you should be able to like figure out within questions that, okay, where can I apply what? And we'll do some more questions come tomorrow, and we'll also cover like polygons, and then obviously we'll move across the rest of the geometry like circles and coordinate, etc. Yeah. Okay, guys. Hopefully it was a helpful session. Hopefully you learned something new from this. We'll connect tomorrow, potentially earlier than today.
So you will tell the time on the group?
Yeah, we'll notify. Like what? Okay, now that most of the people are here, right? Like what time works convenient for you? Like obviously, completely understand that like people would have Sunday plans with family, friends, etc. But like what time works convenient? Like, would like
So
7 p.m. be a
I
convenient time to
think
start?
the same time would be convenient because it was earlier known, so planned everything according to this time. That's why. So
Okay, so fine, so cool. So actually 8 to 11, then we can keep it if that works, right? 8 to 11, 11:30
that's
or
not
something.
issue. Yes. This time to 11, if it extended, it's okay. But if
The
it
start
starts
time.
earlier,
Yeah.
early and all, it would be problem. That's it.
Okay, no problem. So, but then, yeah, tomorrow then let's sort of gear up for a longer session, right? And we'll again continue some more good level questions and some good applications of the concept that we've learned. But thanks a lot, guys, for bearing with me here, and appreciate you going through this with me.
Thank you, sir.
Thank you, sir.
Thank you.
Okay. Thank you. Bye.